Good afternoon, everybody. I am very sorry to be too late today, but the second session starts finally. I would like to first of all to thank everyone who spent effort and support to this conference organization and make the contribution with their presentations. Although session may seem very long, but I am sure that you will not get bored because the session contains very valuable estimated speakers and very valuable presentations. We start this session with the presentation of my dear friend, Professor Dr. Asif Ali Qureshi from University of Engineering and Technology, Lahore, Pakistan. And Dr. Qureshi graduated from the University of Engineering and Technology, Lahore, Pakistan, and then take his MSc degree from University of Engineering and Technology, Lahore. And then he took his PhD degree from University of Auckland, New Zealand. And his interest area are the intrinsically conducting polymers and membranes development from the processes, polymer rheology and the processing and materials characterization, electrochemical and mechanical chemical characterizations. Please switch on your microphone and camera. Dr. Qureshi, are you here? Dr. Qureshi.
Good afternoon, Dr. Irfan.
Good afternoon. Welcome. It's a very great pleasure to see you here again. Would you please open your camera and the microphone?
Yes. Am I visible to all of you?
Thanks. Now I switch all my camera and microphone. Would you please start your presentation?
Okay. I will share my slides just now. I'm going to share my slides. Yes, Professor Irfan, are my slides visible now?
Yes, it's very clear. Would you please start?
On your call, I can start anytime.
Before that, I want to remind you that your presentation will be recorded and also simultaneously published in the YouTube. Okay?
Sure.
Please start.
Thank you. Thank you, Professor Irfan, and welcome all of my colleagues and peers I will talk briefly on cation exchange membranes based on intrinsically conducting polymer that is polyaniline, usually we call penny. So the title is Novel Heterogeneous Cation Exchange Membranes Synthesized Using In situ Diaphragmatic Deposition of Polyaniline or penny. Uh, my name is Asif Ali Kaisar. I'm a professor and chairman of Department of Polymer and Process Engineering, that is of University of Engineering and Technology, Lahore, Pakistan. Right. A brief introduction of membranes development. So the first breakthrough was 1963, the dawn of the commercialization of membranes from Dube and Rajan work uh, from asymmetric membrane synthesis, and that generated or originated later on spiral bond module and hollow fiber modules. Uh, uh, these are the commercialized modules. These were started using back in 60s. And then we had ultrafiltration, microfiltration membranes. Then came interfacial composite concept of membrane morphology, gas separation, hollow fiber membranes, and in this century, the more application towards industrial processes like vapor separation and pervaporation, and some other functional applications of the membranes. Uh, Membrane, depending upon their nominal pore size, we can classify into various morphologies, types, means, and also in various processes. So, on the larger pore size or large pore size, and we have microfiltration. At the interface, we have ultrafiltration, and on the another extreme, we have pervaporation and gas separation membrane. These are virtually dense membranes or non-porous membranes. So the mechanism also it does shift from pore diffusion mechanism in the mechanism of permeation. Uh, from microfiltration, that is pore control mechanism, to solution diffusion mechanism in these dense membranes in processes like evaporation, gas separation, and RO, that is reverse osmosis processes. We are talking about ion exchange membrane. These are charged barrier membranes, dense membranes, uh, but these are in their solid state while in the electrolyte solution. So the basic idea is very simple that we have a charged barrier and we have electrolyte. This ion exchange membrane is interposed between two electrodes, cathode and anode, and these electrodes attract their counter charges from the electrolyte or ions from the electrolytes, and this uh, middle barrier, that is the ion exchange membrane, it excludes the similar charge. So if it is a cation exchange membrane, uh, it will exclude negative charges, and it will allow the positive charges to pass through, and vice versa for anion exchange membrane. For membranes, uh, are my slides visible, Professor?
Yes, it is very clear and visible.
Right, thank you. So we characterize ion exchange membranes through various parameters, that is transport number, ion exchange capacity, then stability, chemical and environmental stability, and then linked with the ion exchange capacity is water uptake. So a few ion exchange manufacturer in the world, we have Asahi, we have DuPont, and many others, just to give an idea. Then we talk about intrinsically conducting polymers or electroactive conducting polymers. These are the polymers which are electronically and ionically conducting based on their chemistry, based on their chemical structure. Usually, this structure is a conjugated structure. Very well-known conducting polymers we are familiar with are polyaniline, we talk about polypyrrole, we talk about polyacetylene, polythiophene, and the conductivity, if we see this figure, it lies uh, in mostly in semiconductors range if we compare with the metals and semiconductors. So, but as we can see, there is a big range of conductivity variation. That depends on the oxidation state and doping state of these electroactive or intrinsically conducting polymers. So we can tune or we can control the electrochemical properties and the conductivity as well by adjusting their controlling their oxidation and doping states. There are issues of mechanical properties, stability, poor processability. These are infusible and intractable polymers, uh, and doping immobility. The dopant is not very stable in water and electrolytes and solvents. So doping immobility is a big issue. So we have these ICPs conducting polymers with some issues. These hamper their commercialization till date. Yes. Based on their properties, ICPs or intrinsically conducting polymers, these can be used and these are tried in various applications. When we talk about membranes and ion exchange membranes, we usually make use of this ion permeability and the charge on these films of conducting polymers, and these act as uh, ion exchange membrane or barriers. So we use mostly here in our laboratory, that is polyaniline, that is a promising intrinsically conducting polymers. It has very clean synthesis both from electrochemical and chemical oxidative polymerization of monomer. Then we can tune or control the various oxidation states and doping levels of polyaniline. In fact, as this diagram shows, we can switch uh, among various oxidation and doping states. Uh, and we can have the properties of our requirement. So based on these properties, these membranes based on polyaniline, these have potential application, or these have been shown with certain potential applications in, for example, charge-based membrane separation. So, in this particular study of 2019, polyaniline particles were embedded in thermoplastic matrix, and resultant transport number studies showed very high transport number for monovalent uh, Na, both in NaCl form and in sulfate form, and also the rejection of uh, uh, this in terms of transport number. We can compare this right hand diagram. It shows ion exchange capacity linked with the water absorption content of the membrane, and these all vary depending upon the additive content, and that is the polyaniline incorporated in a thermoplastic matrix. Similarly, in organic separation, in organic nanofiltration, we have uh, uh, this asymmetric, highly asymmetric morphology, where we have non-porous skin layer at the top, uh, and then we can see the separation factor or separation ability of this membrane for two different solvents like U-boil and uh, some low molecular weight solvent weight. Uh, in electrodialysis, we have again a complete history of the development uh, from starting from the concept, very basic concept of electrodialysis up to the first pilot plant of brine desalination. Polyaniline can be deposited on base membrane when we use modified membranes, modified with electroactive polymers. We can use various techniques. Here we use mainly the solution polymerization, where we dip the substrate or base membrane into the polymerizing solution of aniline monomer and some oxidant, and the polyaniline it is deposited in situ on the substrate. But we have another very promising technique, very should I say excellent technique, that is a two compartment cell permeation. What we do, we take two compartments and we interpose the base membrane in between these two compartments, and one compartment contains the monomer aniline, another the oxidant, and these two component of this polymerization reaction, these permeate through the membrane, these pass through the membrane, and somewhere in between the membrane, within the bulk of the membrane, these polymerized, and we have polyaniline that is intercalated within the membrane matrix. So this is called what we call as diaphragmatic polymerization for in bulk deposition of polyaniline. A quick overview of what we have done recently in our group here, uh, in our department. We synthesized these heterogeneous membranes, uh, ion exchange membrane. So first we coat the ion exchange resin with polyaniline, and then we put this uh, modified ion exchange resin, cation exchange resin, into PVC matrix, and we got a very high level of separation and ion exchange controlled or tuned ion exchange capacity. Transport number based on various content of polyaniline deposited on that resin. A clear uh, separation between monovalent ion and divalent ions, cations, through electrodialysis uh, that had been observed in this sort of membrane. Then we had nylon and sulfonated silica composite membranes with polyaniline as a top layer, that was for evaporation of ethanol water mixture. Uh, we use again the simple solution deposition technique, and from this you can see we got a good selectivity finally for pH 66 embedded silica particles and polyaniline as a top layer. Very stable membrane with good separation. Another one was polyaniline polyimide thin film composite TFC membrane. So we got a clear morphology with a dense polyaniline layer at the top of ultrafiltration polyimide base, and we use it for again for vegetable oils and solvent separation, study in nanofiltration, and we got good uh, rejection and the separation too here. And then polyaniline deposited for pervaporation membrane on polyurethane. Uh, Pervaporation using ethanol water, and again we got some good results in terms of flux and separation factor uh, at various feed compositions, temperatures. Uh, for this particular study, that is heterogeneous membrane of ion exchange resin, that is PSS DVB. embedded into TPU metal, thermoplastic polyurethane, and then modified with polyaniline. And the main point, as I mentioned earlier, is that this polyaniline is deposited within the membrane bulk, not as a only surface layer. So it is very much there in the membrane bulk. So this is synthesis for this membrane. So this is two compartments. So this is base membrane, aniline, monomer, and oxidant, and uh, the intercalation, in situ intercalation and polymerization within the membrane bulk. Again, synthesis details. So we have finally a variable morphology based on this diaphragmatic polymerization time. So at 8 hours, we varied from 2 hours to 8 hours, and 8 hours we had a significant content within the membrane bulk, and also the surface deposition as well. So if we see the penny integration level for 8 hours, we got 24%. That is very significant. And we have a clear change in the membrane morphology as we were at the time of polyaniline deposition. Uh, that was stability curve. As we increase the penny content, we shifted behavior from TPU thermal degradation to polyaniline dominated degradation here. Similarly here, ion exchange capacity. As we increase the polymerization time, we had a loss in ion exchange capacity. Uh, the the synthesized unmodified TPU ion exchange resin membrane, which had ion exchange capacity around 1.35 in these units milliequivalent per gram. That dropped to 0.97 upon 8 hours. Yes, that is understandable. Uh, as this content increase polyaniline, we have initial drop in the ion exchange capacity. Yes, membrane potential study. So for transport number here, this is a very significant result for variable polyaniline deposition time for mono and divalent ions. uh, what we have an increase in generally an increase in transport number by increasing the penny deposition time or content, you may say. But here we have a point at 2-hour polyaniline deposition where we have a big difference uh, in the between the transport numbers of monovalent and divalent ions. So this is very significant and very interesting here. And based on this, uh, when we measured the separation efficiency in a three-compartment uh, electrodialectic setup, we got some these results for monovalentine and for uh, divalentines. The separation efficiency, uh, the number that is rejection for monovalentine, you see we got as compared to this, when we compare this, uh, that is the 44 for voltage across the cell when we maintain the 10 volts. So we got the maximum difference in the separation efficiency of both monovalent and divalent. Thank you very much. That was a brief overview of what we are doing at our department, and also particular to this novel membrane system. And I shared a few results briefly. I hope what I wanted to convey, I have conveyed. If you have any question, you may please ask.
Thank you very much, Dr. Krasir, for your very nice presentation. Also, Dr. Atesh, want to thank you. Dr. Atesh?
Dr. Asif, thank you very much for your this good and informative presentation. We are very happy, all of you, all the professor here. Thank you very much.
Thank you. It's pleasure to me, and thank you very much.
Now, I'm looking for is there any question? Although we do not have the sufficient time because we start very late to this session. Therefore, we may only take one question, and I want to use this right for me. If there is no any other question, I want to ask especially for the cross-linking of the cross-linking agent. Because you know that the swelling is a very important problem for the membranes. And on the other hand, we have the optimization between the selectivity and the permeability of the flow rate, in fact, the flow rate to the membrane. Therefore, the degree of cross-linking is very, very important. How did you adjust it to the desired value? Because you know that the cross-linking is very important for the mechanical stability point of view. And also it decreases the molecular space within the membrane matrix. Therefore, you have to adjust very well the amount of cross-linking within the membrane.
Yes, yes, I understand. I should say that we didn't play much with the cross-linking or cross-linkers content or cross-linking level, nor we properly characterize the cross-linking level in our. We actually use cross-linking mainly for, as you mentioned, in our solvent separation for evaporation membranes. But we didn't experiment much on this. Just what we did, we immersed those membranes in that feed composition of solvent and water or two solvents. And when we found a reasonable stability in the membrane, just by immersing it for certain few days, we took it as the workable cross-linking for us, because there were many other variables involved that that were controlling this trade-off between permeability or flux and the separation. So we were more towards those variables. But in future, yes, it is very important parameters. And when we are going to fully or we are going to see the commercial potential of these membranes, we have to optimize the cross-linking level as a main parameter as well. Yes, true.
Thank you very much. And have a nice day. We have the second speaker, Professor Dr. Hüseyin Şehitoğlu. He took his Bachelor of Science from the City University of London and took the first class honors. And after that, he studied at Theoretical and Applied Mechanics, University of Illinois. And his research area are the applied physics, energy, health and biotechnology, security and defense, solid mechanics and materials, and transportation.
Right.
Professor Dr. Şehitoğlu has significantly advanced scholarship related to thermomechanical fatigue, fatigue crack closure stress-induced phase transformations, cyclic radiating plasticity, sleeve anti-winning in metals, and the Dr. Şehitoğlu's website is High Temperature Materials Laboratory, which deals with the publications, presentations, and the research equipment. I probably invite Dr. Şehitoğlu. Please switch on your microphone.
Thank you. Can you hear me? Can you hear me?
Yes, very
Very good.
clearly.
I'm going to share my screen.
Of course. Please.
I hope you can see my screen.
Yes. Your
Great.
screen is very clear.
Thank you very much.
Clearly.
It's an honor to be part of this meeting. I thank the organizers and also the session chair, Professor R. And also I want to thank Professor Hakan Ateş for inviting me. I want to talk about shape memory alloys and some of their applications and some of the work we're doing in this area. I have a number of students who worked in this field. A number of them are in academia. The ones in green, Kangal, Ibrahim, Karaman, Demircan. Demircan is in Koç University, Karaman is in Texas A&M, while Abu Zaid is in United Arab Emirates in Sharjah, and Sertan Alkan is in Boğaziçi University. They're on the faculty. I had other students here in the blue, and my current student is Samir Mohammed, who's working on in this area. And my website, as Professor R mentioned, is this HTML mexiillinois.edu. I have all my publications there if you wish to look at them. There are some presentations and videos there as well. I'm thinking I should go to the full screen mode here. You could see this, right? Better? Can you see my screen?
Yes.
Yes.
Oh, great.
It's
Okay.
better now.
Now, I want to talk a little bit about basic definitions because this is a very general audience. And then I want to talk a little bit about some examples and some theoretical developments in this area. First, I want to talk a little bit about twinning, slip, martensitic transformation, introduction to shape memory materials, some examples of stents, ankle anchor, elastocaloric cooling, high temperature actuation, and reinforcing spirals. So the stents and ankle anchor is used in bio applications, of course. Elastocaloric cooling is kind of a new development for using shape memory alloys as like refrigerants. And high temperature actuation and reinforcing spirals are more for structural applications. So this slide is a summary of what I just said. The biomedical applications, the majority of the shape memory materials are used as cardiovascular stents to open our arteries. They are used, I'm going to show a movie about how it's used as an anchor lock in the body. And then these are some of the high temperature applications in torque tubes and in jet engines. And also it's used in automotive applications as well. Now, those are the application side. From the experimental standpoint, these materials are not that simple. They have, they can be studied, of course, at a quantum level, at the electronic level. There are complicated energy pathways for the transformation, going from one phase to another. And there are internal precipitates, that's at the micron scale. And there's a crystal lattice change from a cubic structure to a monoclinic structure as shown here. One can try to do molecular dynamics to understand the behavior of these materials. And then at a larger scale, of course, one can experiment, try to understand their mechanical behavior and make measurements of internal strains. And you can identify the phases with various diffraction methods. I will mostly talk about, of course, the microstructure, the modeling, but I will show examples of the applications as well. So this is a description of twinning. What is a twin? It's a reorientation of the crystal in a material. In this particular case, there is no phase transformation, but when there is phase transformation, there is also internal twinning going on here. So you could see here, this is a very simple cubic lattice, and this region here is the twin region in the middle. And in real materials, it's a little more complicated because it's not a pure material. There are different elements involved. So this is the twin plane here, and that's the three-layer twin. But in addition to the shear, there is also shuffling of the atoms, as you see here. To get a mirror symmetry across the twin plane, the atoms have to shuffle, so they are in symmetric positions, as shown here. This is more common, of course, in real materials. This is kind of an idealized picture for a simple cube. And the energy landscape can be a bit complicated because if we plot shuffle vertically versus shear, and the way the shear and the shuffle occur simultaneously it needs to be determined. This is an energy landscape here, and you could see here the minimum energy path is not a pure shear or a pure shuffle, or it's not a simultaneous linear combination of shear and shuffle, but it's a kind of a complicated shear and shuffle occurrence, simultaneous occurrence that needs to be determined. This is very similar to the picture here the movie that I showed here. This is in nickel titanium. So you could see here there are nickel atoms in the blue and the titanium atoms in the gray. To accomplish internal twinning, and one needs to go through a shuffle process here. You could see here there's the overall shear where the twin inside the material is growing, but you have to also simultaneously get some sort of a shuffle to achieve symmetry across the twin plane. So I mentioned that twinning is part of the phase transformation, but it's more complicated than that because you could have interaction of the different twin systems. You could see here there's a twin system 2 that's active here. It reacts with twin system 1, and there is some reaction here. This is a dislocation, of course, and then a new dislocation results. So these interactions, have to be studied, understood to be able to characterize the material. This twinning mechanism that occurs during phase transformation is not only in shape memory materials, but it's in many different materials. Of course, they are even in superconducting materials, magnetocaloric materials, and various materials you're getting twinning deformation. The twin migration stress, as to move this dislocation, is a key parameter, of course, as the dislocation moves along the twin boundary. So I mentioned transformation, I mentioned twinning, and I mentioned also slip. So this is probably known to many of you. Slip is motion of atoms over other atoms. And depending on the crystal structure, in this case, we are looking at a body-centered cubic structure. You have these slip planes, and then within the slip planes, you have these you have these slip directions are like this, and these are all the slip planes that are listed for the body-centered cubic case. And this is also another picture of the dislocation here. And as we apply shear stress, the dislocation moves from the left to the right, and finally emerges on the surface as a unit step of slip. So we have discussed slip. We have discussed how dislocations move. Instead of breaking all the atoms, of course, you have an extra line of atoms here. So only the bonds near the dislocation are broken. So it's easier to move the dislocation than in the entire crystal, because you have a smaller volume to move at a time, but then the net movement is shown in here. It's just like the movement of a carpet or a caterpillar with a hump. And the slip is manifested in the material as such. You get this is the grain structure here, and then you see the slip bands here that are forming. So this is a very common occurrence. It occurs during phase transformation as well. We discussed twinning, we discussed slip. We're leaving the last item, Martensitic transformation. Of course, we are familiar with phase transformation. Materials can be in the form of solids, liquid, or gas, depending on the pressure and temperature. We are in the shape memory field, or in metals, we're talking purely solid to solid phase transformation, solid 1 to solid 2. You go from one crystal phase to another crystal phase. A very classical example of this is the hardening in steels, and how people have already known for centuries that phase transformation can harden a blade, a sword, from a pure iron to a hard pearlitic phase. But then the martensitic phase is where you're getting transformation from one phase to another. So that's an example of a solid to solid phase transformation. Okay, a different crystal structure. In this case, of course, it's not shape memory material. In the shape memory, as I will indicate, the transformation is reversible, but in steels, it's irreversible. This is a typical example of how it happens. Sorry about that. So you start with let's say in this case, it's a cubic to orthorhombic transformation. This is a titanium, like a titanium niobium alloy. You have a cubic crystal here, and the atoms move here, they shuffle into these positions here, and you get some sort of a hexagonal close pack crystal, and then you compress the crystal in eta1 this way, vertically, and then expand it horizontally, and you end up with a fully orthorhombic crystal. So this is an orthorhombic crystal. Originally, you start with a body-centered cubic material. So this is one type of transformation that's studied in titanium alloys. A good way to show this in a movie is, these atoms. This is initially it's body-centered cubic. It moves into this middle position here. That creates a hexagonal close pack symmetry, right there when the blue atoms move to the middle, and then that's the HCP nucleus, and then you compress it. That it goes through a compression in the O1 direction, and a slight expansion in the 1,1,0 direction, and then that actually is the fully formed HCP. Orthorhombic is one more step after that. So the premise of the shape memory materials is really, excuse me, is the following. So you go from one phase to another. This is stress, this is strain, if you like, and then you remove the load, and it comes back to the original shape. It can happen as a function of temperature, but after some finite temperature, at higher temperatures, you get primarily plasticity. So you don't get shape memory errors, but this is the shape memory behavior. For those of you that are in a slightly different field, you could think of this as a force, and this axis as displacement. So it's like a rubber type behavior, but it's a metal, of course. This is called superelasticity. This is called plasticity. Now, there's another behavior called shape memory effect. So in this case, what happens is you're in the martensitic phase, you deform it, and you unload it. It doesn't, it stays martensitic, but then if you heat it, then it recovers. So that's called shape memory behavior, okay? This is a typical simulation of superelastic behavior. This is in nickel titanium. So you could see the martensite that forms the second phase, this phase here, and then it's actually internally twinned. The martensite itself is internally twinned. And then when you unload, it goes back to the original structure. So you can absorb large strains, like this is 5% strain. This is stress versus strain here. And it has potential applications, of course, for absorbing shock, for example, but it's also used in biomedical applications. So that's the superelastic behavior, this one. And this is like an actuator behavior. So what you do is you keep the stress constant at some value, and you cycle the temperature. And you could see as you cool down here, you go from austenitic phase, higher temperature phase, to a lower temperature martensitic phase. And the strains can be quite large, at 8-9%. Again, for a metallic material, this is quite high. And you could see this is a high temperature shape memory material. This is nickel titanium with hafnium, and you can operate this at higher temperature. This is like actuator behavior in the sense that what they do is they put an electrical current through the material, and it cause an increase and a decrease by applying a current, and you could use it as a actuation rather than using hydraulic actuation. You could use this actuation, which is more in many regards. It can be done in a much closer space, without the need for a hydraulic fluid and all that. So this. If I look at these images, we're looking at internal strains here, development, etc. But the strains can be as high as 8-9%, and they could recover. This is a typical image or a movie of an experiment where you're studying the superelasticity. This is stress against strain. You could see the new phase is formed here, and then yet another new phase is formed here. So this material in this case goes through successive two different phases of martensite. So this is the first phase. This is another phase, but they both recover upon unloading. This is stress again. This is strain, and the strains are extremely large actually for a metal, 12-13% recoverable strain. So you can imagine this could have a lot of potential applications. Of course, our work is primarily to understand what's going on, how this transformation occurs, and we're looking at here typical example here. We're looking at martensitic phase and an austenitic phase, and there is an interface. So this is martensite here, and this is austenite here. You know, this is the parent phase. This is the martensite is called sometimes the product phase, and you apply the load as we said. This material, this martensite grows, and at the interface you get obviously dislocations. The motion of the interface is linked to the motion of dislocations, which are reversible for the superelasticity case. And you could see the dislocations have a certain spacing at the interface. We're calculating this spacing of the dislocations, the nature of the, this is the Berger's vector of the dislocation here. This is at the austenite martensite interface. And this is actually a high resolution transmission electron microscope image of that interface. You could see it's a stepped interface. It's not a terrace. It's it has steps, and it has these disconnections, and it has these terrace areas. So there's a bit of detail there that needs to be understood. And what we're looking at is determining these dislocation patterns and how they evolve. And that, in this particular case, the austenite is the B2 phase. That's a cubic phase. The B19 prime is the monoclinic phase. The monoclinic is a lower symmetry crystal. So there's a significant difference, and that's the way the atoms are arranged at the interface. So one of the things we're trying to understand is this critical result shear stress for transformation. How much stress do you have to apply to get this transformation to occur, how this superelasticity occurs. And we find, of course, that depending on the crystal orientation, in this case 111 versus 110, let's say, we find the differences in the stress level. So the stress level depends on how the material is made, how the crystal is oriented, and as I mentioned here, this is the interface here, and that's the austenite and that's the martensite. Now, if we, excuse me, well, here if I look at these closer, so closer to that interface, what I find is that that interface, as I said, is a stepped interface, right? It has a step like that. So you see it's moving step by step. And this is an example of where the martensite is growing into the austenite. So that these steps here that are shown in these atomistic simulations are the interfaces that are also shown in a schematic up here. And our aim is to calculate the stress at which this occurs. So there are no really empirical constants here. We are determining the critical result shear stress for forward transformation, and that is some of the results we have. We have some experimental results also shown here, and the trends are very similar, of course. I wanted to show you my original diagram again. I want to talk a little bit about the applications. The majority of the application in these shape memory materials is in biomedical, in the stents. So the nitinol in medical devices, it's a fairly new development, of course, a relatively new development, started in the 1970s. They started using these stents in the 1990s, and they are used as heart valves, filters, various devices in the body, and it's a big industry, no question about that. It's the way that it works in the stent application is you take the stent, you compress it, right? You like this, and then you deploy it inside the vein. And what happens there is that, you know, that's the stress strain behavior. You're when you deploy the stent, which is the expanded, once it's expanded inside, it has high stiffness, you know, in one direction, and low stiffness in the other, in the other direction. So it puts a gentle pressure on the arteries, but it will not collapse. It will not collapse inside the stent. So it puts this pressure to the arteries, which would be this pressure basically here, the one that's shown in here. But it's deployed. It's used in this particular state here. I just wanted to point out that the nitinol, that it's called nickel titanium, of course, alloy, the literature has grown significantly in this area, in the medical literature as well. A relatively new application is in this fusion of the ankle. You know, people have ankle injuries, or as they get old, as we know, this fusion in the ankle gets compromised, and people have used these screws, and those have got looser over time. You know, the tension in that's applied. Well, actually, in this case, you're trying to squeeze them, so the compression that applies decays over time, and then you get what they call a non-union. So they are not, the compression is lost over time. And so they have used the different screws and tried to anchor them there. The shape memory material is an application here. What they're using, what they're doing is they're applying. What they're doing is they are applying. They're using this shape memory rod in here, and they're basically applying a nitinol element inside, and then they're pulling that and then anchoring that. And over time, so they're pulling this device, and they're anchoring it here. They're pulling it like that, and then they're anchoring it. And so there is always a constant force in here. And then they attach it with these screws here. And this is different than just applying a static screw here. So over time, this compression here is maintained, as opposed to losing it over a period of time.
By combining the sustained compressive power of external fixators with the low profile and rigidity of intramedullary nail.
So what happens is that the compressive load that is maintained in that ankle remains for as the bones go under resorption, the regular nail loses compressive force, but the dyno nail, in this particular case, appears to maintain this is the using of the shape memory material, superelastic material here. That's the arrangement that applies the compressive force, and over time it doesn't decay. Another application that I mentioned that's become very, very popular in the last few years is use of shape memory materials is potentially for elastocaloric cooling. So, we typically go through go through a pressure compression cycle to cool for air conditioning purposes. And this is showing the phase diagram associated with that. There are, of course, refrigerants that are used here that are harmful. So one possibility is that came about is the use of shape memory materials for cooling purposes. So this is the pressure enthalpy curve for this case. This happens to be a small device for air conditioning purposes, for cooling purposes. But all these devices are using refrigerants that are not friendly to the environment. And so what happens in the shape memory materials, in some shape memory materials, is that this is your stress, this is your strain here, and this is your temperature. As you go through the phase transformation, the temperature increases slightly. Not too much in this case. But if you unload here quickly, as we're going to see here, relatively fast, and you see the temperature dropped here. So if you put your hand in there, you try to touch this with your finger, you'll feel the cool. So one possibility is here we're going from like 10 degrees, almost 10 degrees. There are examples of this drop in temperature by rapidly unloading. So it's like an adiabatic condition here and if I may show this one more time here. So if you deform it, when you go from austenite to martensite, it naturally is it ejects heat, but a little bit. But if you cool it relatively, if you unload it relatively quickly, then sorry about that. We are seeing a change in temperature, and this may replace some of the very expensive materials out there that are used for cooling purposes, such as these exotic materials. The nickel titanium, which is a shape memory material, can produce cooling as much as actually here. This diagram is a few years old, so it can go up to maybe about 20 degrees Celsius, one can cool. And that can happen over a wide range of temperatures. So we've looked at nickel titanium, we have looked at cobalt nickel aluminum, we've looked at few alloys. And this black one is copper zinc aluminum. That's also shape memory material. And these are the more well-known materials that are not shape memory materials, but that are used for magnetocaloric cooling and things like that. And they are exhibiting several degrees, but they are very brittle materials and they cannot be easily incorporated into structures. But they are widely used. Some of these alloys here. The shape memory ones are. These are some of our results for nickel titanium. That's the best, copper zinc aluminum, and really apologize for the jumping here. And the nickel, this is the delta T elastocaloric effect as a function of temperature. You could see the effects in tension and compression. As I mentioned, it was as much as 18 degrees. So in compression, this can be used many, many times because the material is not going to fail. And people have been trying to build devices, for, let's say that you move the shape memory material in from tension, unloading, and then you use it, you move it from a cold to cool something, and then eject the heat here and then cool back here. So they have built some devices, and they have built ribbons of nickel titanium. They have obviously is transferred to source and sink by solid to solid contact. So there's a source and sink in here. This is another potential application where they are, there's a air inlet on the hot side, and they're rotating these wires, the shape memory wires, and then it cools down, and then you get the cold air coming out from the outside. So they have built some devices that could create, all one has to do is to rotate it. So when you rotate it, this wire goes under tension and then compression, and then it goes through basically a super elastic cycle, and then you could eject heat. The other applications of the shape memory are in the potentially in the flow control in aircraft, in jet engines. And as I mentioned earlier, you can apply electrical resistance to move these foils, and you can streamline the flow. Another interesting application that came about in the last few years is to use these shape memory materials as wheels, as tires in the wheels of vehicles, like in Mars. You don't want a flat tire, but in a very rough terrain, these shape memory materials are used as a tire to make a tire. These are the wires of shape memory material, and they can go through a very rough terrain without the difficulties we would get in a regular rubber tire. So this is another application of shape memory materials in reinforcing concrete, for example. And one of the issues is the large deformations that occur under earthquake conditions. And it's been proposed that you could take the shape memory materials and use them as spirals around the concrete beams. And you could do before heating and after heating. After heating, you put a compressive force in there. And this is a test where you have a concrete column reinforced with polymer, and this is the one with the shape memory material. So this can absorb considerable amount of displacement, and the integrity here is much better. The structural integrity is much better with the shape memory material. Here you could see the fracture occurring here at the base here. Here there is no incipient fracture at all. This is nickel titanium niobium shape memory material. And this is a summary. Of course, this is still a bit complicated, but superelastic behavior here. And this is the actuator behavior. You heat and cool, and you go through the strain forward and reverse directions. This is the shape memory effect, and that is, you deform it and then you heat it and it recovers. This concrete application is in the constrained recovery phase. Here you basically maintain some stress level there, and then there the displacement is fixed, but upon heating and cooling, your stress goes up and down slightly like that, heating and cooling, but nevertheless it maintains the integrity of the structure. So I'm checking my time here, and I think I have a few more minutes left. I wanted to say that there are a number of papers, of course, on everything I've talked about. And finally, I want to say that the bedrock of material science is the idea of a critical shear stress law. This is what's taught in undergraduate classes. You apply a load, you have a slip plane here, normal slip direction M, and that if you calculate shear stress on that plane in that direction, that has a unique value. It's called critical result shear stress. It turns out, of course, in these materials, there is no such thing. There's quite a bit of dependence of the orientation. Okay, and these results are for tension. These results are for compression. So there's quite a orientation dependence, crystal orientation dependence. A lot of the materials that are used in biomedical applications, etc., they have 1-1-1 texture. So in the polycrystal materials have 1-1-1 texture, but in general and polycrystalline material, you could have all these possible crystal orientations. So some grains may slip more readily than the others, and we need to understand that. So it is to do with the dislocation motion and the core of the dislocation. This is the differential displacement map showing the displacement at the core. This core, if it is small, it gives you a higher strength. If it is large, it gives you a lower strength. And this is kind of taught at undergraduate classes as well. But the thing is, this core is the way that core width is decided is not based on just the critical or one shear stress component, critical shear stress component, but other shear stress components can affect the size of that core. And that's what could create this large tension compression asymmetry, which is known in shape memory materials, as well as orientation dependence. And this is the prevailing glide shear. But we should point out that we are doing anisotropic elasticity with Eshelby straw formulation, and then we're relaxing these core structures. We're applying stresses, and then recalculating these core structures and deciding if the dislocation will translate. If it translates, we establish the critical result shear stress. If not, we have to increase the stress and try to determine what that critical result stress is. So as I mentioned here, that's the core behavior here. That's the location of the dislocation. These are the displacements. That is based on an Eshelby straw formulation. We point out that this maps of these displacements are, it's a screw dislocation, so the displacements are out of plane. And that's what's shown here, UA, UB, these are out of plane displacements. And these displacements that are plotted are with respect to the center here. So, what we're looking at, of course, is this is the glide shear stress, and these are the non-glide components. If we apply a non-glide component, it affects the core, but our classical description of critical result shear stress does not account for this non-glide component. You could have non-glide shear stress, you could have normal stresses as well. Those affect the displacement, the core behavior of the dislocation. And though that's the applied stress part, the tau is the glide component, the sigma is the non-glide component here. So there's effects of that. And then we could see here, for example, the 249 compression case versus 249 tension case. This is the core shape and the core displacements are fundamentally different. And in general, we could have normal stresses and we could have non-glide shear stresses. And you could see here, you know, the core is not fixed, it's changing, and one needs to account for that. If we look at the 249 compression, that's a wider core than the 249 tension. And if we look at the results here, originally, the 249 compression is here, 249 tension is here. So the wider core gave you a much lower stress than the skinnier core. I'm almost done. That modifies our yield criteria. This is the classical yield criteria that we teach, the Schmidt law. The generalized yield criteria is different. It looks a bit more like like a Concorde airplane, kind of a look. That's sigma 1, sigma 2, sigma 3, as are the principal stress components. As I mentioned, this is martensite, this is austenite. We have dislocation at the interfaces. We are studying these interfaces now with modeling. We want to understand how the forward and reverse motion of these dislocations. This is the habit plane. This is austenite. This is martensite. These are the internal twins inside. These are like internal twins inside here, and these dislocations are moving forward and reverse. The way the shape memory occurs is that these dislocations move back and forth, and readily, if they return to their original positions, then we have full recoverability. So we are interested in the slip, Berger's vector of the slip, and then the twin system, the twin planes, etc. there. And then in the reverse case, if they get jammed at the interface, then you don't have the full recoverability. So one has to understand, if they get jammed, you also emit slip into the matrix, and then you get these dislocated areas. So that prohibits recoverability or the shape memory effect. And we are interested in, as I said, these interfaces, how they move. I showed some pictures of these earlier. This is a twin interface in this particular case. It is a combination of shear and the shuffle of the atoms. And that's the way the twins move, and the phase transformation ultimately moves. Just showing one more picture finally of the interface here. These are the martensites here. This is the martensite, and these are the slip that are emitted. And we are trying to understand how the austenite martensite interface behaves, how the twinning interface behaves, and upon forward loading and upon reverse loading, any barriers will cause an unbalance in the loading, and then will cause irreversible behavior. I want to conclude, there are many potential applications of SMAs, and there are many new materials. We just, excuse me, we just looked at some of the applications and orientation dependence, and just want to point out that, can you see me? Yes, I hope so. I think I'm frozen there for some reason. Bear with me for a minute. I reconnected my video so that it shows up, but somehow it's not coming on. I don't know why. Oh, I'm sorry, 1 second. All right, there we go. So as I mentioned, we are looking at a theory for incorporating this orientation dependence, which is important in applications, of course. I want to stop here and thank you again for your attention.
Thank you for your nice and fruitful presentation, Dr. Şehitoğlu. We do not have enough time for the questions, but our attendees may ask you questions from the other sources. Thank you very much.
Thank you.
I would like to thank you to Professor Hüseyin Şehitoğlu. Benim hocam, çok saygı duyduğum insan. Thank you very much.
Sağ olun. And best wishes for your symposium. And thank you for organizing.
Thank you very much. You every time support us. Thank you.
Thank you.
Okay.
Thank you very much. Now, our first speaker, I try to connect the Professor Dr. Mr. Ishaki Khan. He is professor in chemistry department at Illinois Institute of Technology. Dr. Khan's research interests include nanoscale science and technology and materials chemistry, that emphasize on functional materials for applications in sensing, energy storage, biomedical usage, environmental cleanup, and industrial catalysis. He has published some 85 research papers in reputed international journals, monograph chapters, review articles, and the 3 United States patents. His research work has been highlighted in Science, Science News, and the Chemical and Engineering News, and incorporated in primary chemistry textbooks. If you can, would you please switch on your microphone and please start your presentation. First of all, I want to remind you that your presentation will be recorded and is simultaneously published in YouTube also. Start. I switch on my
Hello, everybody. Good early morning and greetings from the United States. I know it is a different time where you are. It is early morning, so I've taken my caffeine, so I'm alert, hopefully. Thank you very much indeed for that nice introduction. And let me thank you, the organizers, especially Professor Hakan Atish and Professor Munir Naifa for the invitation. It's a pleasure for me to be here. I would also like to thank the first thing first, a group of talented students and postdocs who have worked for a period of time, whose work, some of which I'm so excited to present here today. Particularly, I would like to mention the recent graduates, Dr. LaSalle Swanson, Kadir Aydemir, who has taken an R&D position after leaving his job at Tubitek in Turkey. So he is back over there. Hopefully he is in the audience. And Ravi Petrov, who actually took a position after graduation at Intel, and Professor Samar Ash. So these are the people whose work particularly will be highlighted, some of them in today's presentation. I also sincerely thank my collaborators, some of these beneficial collaborations, some of them lasting over decades. And last but not least, the funding support for my work from various organizations which are listed over here today. Today I'm going to talk about functional nanostructured materials. Forgive me, I'm a professor, as many of you are, and so just make sure that everybody is on the same page. So let me define what are materials as a chemist. So materials, from my perspective, are the chemical substances that have technical applications or have potential for such uses. And materials in technologies that is needed for making devices that we use in common public.
İki tarafa girmek yani ikili bir bana teşekkür ediyorlar. Ben ikide bir şeycilere teşekkür ediyorum. Şu anda kamerası yok. Oraya bir kamera bulsam. Oraya bir
So I will wait for a second until
oraya ben bir kamera bulayım. Halil Hoca'nın kamerası var. Bu bağlı, ikisi de bağlı şu an. Boşta değil, ikisini de bağlı. Bu şey arasında ben bir kamera var.
All right. So to continue, I was talking about materials which are enablers of technology for making devices that we use on a daily basis. And they are everywhere.
İnternet bağlayamıyorum o zaman. Onu kapatmam
They
gerekiyor.
are everywhere. From
Oradan da
the common household water softeners to smoke detectors, memory devices, computer chips, artificial hips and limbs, joints, pacemakers and batteries. You just name it. They are all consequence of materials. And as we all know and realize by now, that the advancement in the art and science of making materials have greatly enhanced the quality of our lives. One could say that indeed the pace of the development of the industry and society is intimately connected with the advancement in making materials. So while we live in a time of tremendous advancement, there are a host of problems facing the industry and society, some of which are mentioned over here, which were discussed at one of the recent National Academy of Engineering of the USA's grand the problems of the sustainable urban developments, the problem of the staggering needs of clean water,
Alo, Şahin.
affordable health care, and so on.
Duyamadım hocam.
So why?
Benim mi?
While finding suitable solutions to some of these problems facing industry and society without compromising our environment, without jeopardizing our food supply chain, and without contaminating our water table remains truly a challenge. So while the solution to some of these problems would invariably require some calibration and adjustment in our living and consumption pattern. In the meantime, there is tremendous activity in the field of material science and development because it is viewed that the solution to some of these leading environmental and technological problems hinges on the advancement in making high performance, better, newer functional materials, which enable technology. So hence one could say that the materials intimately connected to the industrial developments which delivers to the society the products. Now let me emphasize this point here, that while common person sees immediately the benefits of useful devices which they use and useful products, but sometimes they are unable to make the connection between tremendous amount of fundamental research work that goes on that eventually leads to these products. And as educators, it is our job to bring it in the front burners and continuously emphasize the importance of the fundamental work in the design and development of materials which we do. So the point is that when we talk about materials, essentially we are talking about properties. And we know that structure and properties are interrelated. So the idea is that how to make materials that have desirable properties and functions which are needed for a technology to make devices. So the fundamental thing, the structure and properties are interrelated. Indeed, the structure generates property. So when it comes to the materials science, the central question is this. The most fundamental objective is to produce new materials, is basically the production of new properties. And we know that structure and properties are interrelated. Let me quickly give an example. We know that cisplatin is a life-saving anti-cancer drug. The same number of atoms and similar atoms exactly in the trans molecule, all is same except the structure. Cis is a life-saving drug and trans is a toxic material, useless. This is important point to establish the structure. So the continuous and sustained effort is needed to produce newer materials of the right structures and properties. And this is where essentially our effort lies at IIT, at Illinois Institute of. So at Illinois Institute of Technology, we have been engaged, indeed, I have been engaged at both front. The curriculum developments to produce formal programs to teach materials design and development, and my own active research programs in this area. So before I go into my active research programs, share some of the results, let me tell you the education aspect. We have launched a new professional master's program in materials science, materials design and development, which is an innovative new science degree that prepares graduate in science careers for business, government, academic, and nonprofit sectors. In this program, we combine the rigors of materials design and development with what we call the interdisciplinary business skills. Skills like project management, science communications, intellectual property, environmental regulations, along with simulation and modeling. This is called Science Plus or MBA of Science. Basically, the program fills a gap in the higher education curriculum. This is a program, this was first in the country when I launched it. And this is truly a remarkable thing, since that tremendous development. I have no time to talk about more details about this. This is formal degree program. As for my research program at Illinois Tech, we are actively involved, especially focused on design and development of materials composed of transition metal oxides and their building blocks. Today, I will share some of the results, not all, some of these ones. The key point is this, that to design materials which are sustainable, which are environmentally acceptable, which are relatively inexpensive. And we know the 60% of the periodic table is metals. Oxygen is everywhere, and water is the best solvent. And this is what exactly we do in our lab. Not using any corrosive thing, using oxide as ligand and relatively inexpensive first row transition elements as the building blocks. And you can see in a few moments, I will convince you hopefully that wonderful chemistry could be done just by simply following these green chemistry rules. So in the application part, actually the materials could be used as heterogeneous catalysts, particularly as oxidative dehydrogenation, for example, conversion of hydrocarbons into olefins, which are invaluable industrial feedstock chemicals. Indeed, Kader Idmer worked in this area for the PhD thesis. Another is the removal of NOx gases, which are polluting. The other aspect of the research is NOx sensing or the gas sensing. So it is two-pronged activity. The sensing of the NOx gases, which are pollutant, and converting them into nitrogen and oxygens. Other areas are energy storage and biomedical uses. Today's talk is particularly focused on NOx sensing and slightly on de-NOx catalysis. So let me tell you about NOx. NOx are nitrogen oxides, particularly the mixture of nitrogen oxide, NO and NO2. And they are at a higher concentration. Sustained exposure could lead serious problems. And all those problems regarding the polluting gases is listed here on this slide, which is available. You can see the problem, particularly I'm focusing on NO. This is a very interesting molecule, NO. Indeed, a small concentration, very small concentration of nitric oxide is needed in the body, and body produces it by using enzymes. So this is very interesting. And NO nitric oxide is delivered in the body by exactly bloodstream, hemoglobin, just like oxygen, and body produces it. At the higher concentration, it becomes a pollutant and it's a dangerous thing. My group is interested in both, in the design and development of nitrogen oxide delivery systems at the controlled delivery of NO when needed in biological system, and also in fixing and sensing nitrogen oxide at the higher concentrations. Today, I'm going to talk to you about sensing nitrogen oxides, that is nitrogen oxide sensors formally, and a little bit about the removal in the catalytic process, but mostly about the sensing. So reason being this one. Here is what the sensor, the nitrogen oxide gases are. You can see the main culprit are motor vehicles, about 50%, and rest from other sources. So the reason for this, there is a demand and need for nitrogen oxide sensors and their removals, particularly driven by the environmental protection concerns, which led to the stricter regulations, detection and removal of pollutants, including NOx. Now with the US EPA law in 70s, which started strict monitorings of all these pollutants, most of them and the exhaust has decreased except NOx. Actually, NOx has increased by 10%. And therefore, there is an urgency for finding out the ways and means to remove them, to reduce them, and most importantly, to sense them, to nitrogen oxide sensors. So rest of the talk is about this. The typical NOx sensing that involves the NOx sensors are metal oxides, particularly tin oxides and tungsten oxides, titanium oxide. The problem is that these are high temperature metal oxide sensors. They're called heated MOX sensors, and they require continuously energy. And obviously, if you don't have supply of electrical supply in the rural areas, then out of luck, you use this one. So that is a problem. The desirable sensor properties are high sensitivity, selectivity, that they selectively pick nitric oxide and not others, for example. Their stability could be used over a long time. Reversibility and reproducibility, that after recording a sensor, they should quickly come back and recover. Short response and recovery time, low cost, of course, and small size. So these are ideal, desirable properties. What are the major problems? The drift, inadequate selectivity, their false alarm, and inadequate sensitivity. So there is a cross sensitivity. Again, sensing others and degradation. So what is the solution? Possibly for the new grade of sensor materials. Let me remind you that sensors at the heart is a material. It's a chip made up of metal oxide. So it is essentially the ball game of materials. The desirable thing for such kind of materials is best is semiconductor materials, metal oxides, large surface areas, for example, open framework, room temperature operation instead of 400 degrees C, higher sensitivity and less cross sensitivity, ability to fine tune the structure at the molecular level. This is something which I'm going to show you today that we can do. The other dimension of this problem is the removal of NOx, which is catalytic work. And I just want to share a few slides just where the work is started, but my focus is sensing. I'll not have time to talk about catalytic removal of the gases, but the idea started here. The metal oxide are used essentially for removal of NOx gases. The state of the art is called SCR, selective catalytic reduction. On a good day, that removes only 65 to 80% of NOx, the rest still goes into the environment. And another problem is that it used to use ammonia, which was not an acceptable solution. So we came into this business by looking into that one. What actually motivated us is this, that nitrogen oxide is thermodynamically, it could be broken into its component, which is most benign, N2 and O2. However, this reaction is slow. And therefore, if it could be catalyzed, then you are in business. What actually was an observation by Japanese scientists that zeolites, which are aluminosilicates, when you load zeolites with transition metals, then this reaction becomes fast. However, it is not fast enough to become viable commercially. But the key thing was, from academic perspective, we thought that, well, what is the role of zeolite and what is the role of transition metals? We know that the zeolites are incredible shape selective catalysts. This is aluminosilicates, which exhibit tremendous shape selectivity because of their rigid pore size. However, they cannot do redox chemistry, which is needed for conversion of NOx into N2. That's a reduction process. Okay, so that is they cannot do. However, transition metals, we know that transition metals are incredible redox catalysts. So there are two classes of catalysts: transition metals, which exhibit redox chemistry, and zeolites exhibit shape selectivity. When zeolites alone are used, redox chemistry is sacrificed. When transition metals are used as catalysts, then shape selectivity is lost. We argued that if we can combine both, that is, to marry the shape selectivity with redox chemistry, then this will be incredible. That means we are talking about a new class of materials, and we reasoned that this new class of materials have to be made from transition metal oxides. How to do that one? Rest is all that aspect, and I want to show you our approach. So we said that transition metal oxide clusters are building blocks. They are indeed very useful in the area of catalysis chemical sensing. So we have to make it from transition metal oxides. So what will be the starting material? We said, well, the starting material will be transition metal oxides, clusters, or polyoxometalates. Palms have been known since time of Berzelius. They have been known. Their beautiful clusters have been known, about thousands of them are known. And indeed, a couple of dozens are discovered by my own group. So we said that, well, building blocks are lying in our backyard. Let's use that, starting them as a building block. Now, this is an important point. Until we showed first time that these nice building blocks, they could be activated and shown as a building block by activating surface oxygen. Actually, the chemical community was more using exactly them as prepared, but we showed that they are sitting building blocks. Some of them are larger than molecular weight of small proteins. It's still molecular. You can do wonderful chemistry in this solvent medium, particularly in water, and that was very attracting to us. So we said, let's go and design new material based on these transition metal oxides, but zeolite type. So we went ahead to design a new class of zeolitic material, as we call them. They are not aluminosilicate. They are made up of transition metal oxides. So how to go about this thing? Let me talk to you this, like I was saying, these materials, transition metal oxides, could be made over 60 to 80 to 90% in water from very simple building blocks. And you can see these are incredible molecules. Once you are made, they are rock stable and the large number. So they are incredible building blocks. Nothing surpasses them in terms of building blocks. And there are many already known, and every year dozens of them are added. So what was our approach? We said, let's take, this is a transition metal oxide cluster. You can combine them with a linker. When you use this organic, then it becomes inorganic, organic hybrid material where these nodes are palm. Now, before MAF came on board, they were made already by us by using palm as this one. So they are not simple, the single atom, but they are cluster. So when it is organic linker, then it is composite materials from MAF. When this is inorganic, then it is purely zeolitic material. So here is the cartoon diagram, and here is the truly conversion of these materials. We adopted Teflon pouch approach, where less solvent, less amount of chemicals. You can seal Teflon just like old days in making cigars, cutting and piecing, making cigar pieces. This is, you can do 50 or 60 of these in one reaction vessel. Very efficient. At the end of the day, you can cut this pouch and take out the final products, generally which are crystalline. By adapting this Teflon pouch approach and this approach, which was novel when we published first series of about 24 papers in this area in 90s and about 2010, something like that. Let's taking an example here of one transition metal oxide cluster. Remember that these greens are vanadium, There are 42 oxygen, 18 vanadium, that is 60. This is C60, not C60, there's not fluorine, but it is metal oxide version of exactly that. The shell-like structure, 18 square pyramids joined together. This is at the shell, you can stuff this thing with many of these ions or atoms and molecules, and that changes their electronic properties. The idea is to activate these surface antennas, oxygens, to act them as a ligand. So this is what some of them we have designed, but they were known. So we went ahead and activated them and linked with purely inorganic systems. So you can see this. Recall that this is the same building block. This is intact. Now it is connected with these linkers, inorganic linkers, which are shaded here white or gray. These are transition metal oxide systems or coordination compound. Now this is extremely important. Here, this is basically a nano wire, because these clusters are about 1.8 nanometer to as many as 10 nanometers. So this is the smaller ones, but this is a nano wire, one-dimensional material. You can do pure coordination compounds, linkers, here this time zinc and cadmium and cobalt, and you can expand into 3D. And eventually, it is one-dimensional material composed of well-defined nano clusters. Then two-dimensional materials, these are all new generations. Never before they were known. Eventually, you can have this three-dimensional material. So these three-dimensional materials are very interesting. If you cut a slice of this one, again, the same cluster, what you see is this. I want to take a moment to tell you that if you take a slice, this is like truly zeolitic materials like aluminosilicates, but they are not zeolites. They are made up of transition elements. Not only that, these are transition metal oxide clusters, intact, robust. They are connected by these transition metals. These are active, catalytically active. You can have this as manganese, chromium, iron, cobalt, nickel, copper. You can keep on changing. Now, this is a new approach of what we call bottom-up approach of building new materials from molecular building blocks, where you can go on drawing board and change this. You can change cluster, you can change this one. Now you are looking into this perpendicular to the screen. You are basically looking into rectangular tunnel, which is a zeolitic cavity, and whose walls are defined by, embedded by these active sites. This is a new approach for designing new class of zeolitic materials, which could have the catalyst, the catalytic active site embedded in the wall, which are 100% exposed, and you can change them. This is a non-trivial act in heterogeneous catalysis. Those of us who are in this field, we know that changing catalytic structure at the molecular building at the atomistic level is very hard. Because of the design of these materials, you can do it. And indeed, we have published a couple of dozens of the papers by changing this active site. As you change this, you change the property of the catalyst. The certain of these metals are denox catalysts, which are removal of the nitrogen oxide. When you change this to cobalt particularly, it becomes an oxidative dehydrogenation catalyst. So these materials are not only denox catalysts, but by changing this, actually they become sensors. So it is, we said that this is the two problems of the same coin, actually both sides, and exactly you can shoot them also with the same bullet. So essentially that was the idea, that you can kill two birds with the same bullet by having denox catalysts and NOx sensors. So this is a new class of materials. Again, made from molecular building blocks, and at will and wish we can change their structures. So you can change the cavity size, you can change the active catalyst and the embedded into walls, and all these things are doable at the molecular level because of our building block strategy. So let me show you, there are some other examples, and some of them are so beautifully shown in this one that this is some of these, I mean, somebody printed the Christmas greeting card from the president out of this one, that they look so aesthetically appealing. What you look into these materials, that you are basically looking into three-dimensional crosswork internet structure, the crosswork framework structure, just like in zeolites, except that they are open and transition metal oxide based materials. So what they can do. Okay, before I go into just one example, I can decorate these purely inorganic with organic linkers. And here you are having organic links. Now these are magnetic materials, and with this link you can connect them, and they are single molecule magnet. And there is already a lot of activity in this area. Probably I will not have much time, but I wanted to show you that if you can decorate this with organic linkers, then these are the hook. This is triethanolamine ligand. This is purely an inorganic system, transition metal oxide. I can bring this triethanolamine, this kind of ligand, and replace this oxide with alkoxide groups. 2 arms are engaged with the cluster decorating, so 6 of them, and 1 arm is pendant. So for this, there are 6 metals, each one having a pendant arm. You can see that one. This is functionalized, organo-functionalized. This actually makes the connection of inorganic world with the organic world. Not what it happens is that in this process, this vanadium metal system, they get reduced, 1 unpaired electron and they interact. And so it is a ferromagnetic system. And basically you can see the magnetic properties of this system. What happens is that as you change this central cavity, you can change with just about anything. You can keep it empty, you can put a proton, you can put sodium, potassium, or transition elements. So you can go from manganese to iron to cobalt to nickel. You know, when it is manganese, there are 5 unpaired electrons. These 5 unpaired electrons interact with 6 unpaired electrons here. And this is the magnetic moment of the system. As you go on increasing from manganese to iron, you are pairing electrons. So this is having 4 unpaired. This is having 3 and this is 2. So you expect the magnetism to be decreasing. This is called tailoring the properties of single molecular magnet. Again, very hard thing, but this is textbook example that we have shown. We can systematically do it. And here you see the gradual decrease in the magnetic property. Again, the tailor making of the magnetic properties at the atomic level. This is possible, or they pack like this. Therefore, we said that you can put them together into supramolecular structures. Indeed, you can do that. So these molecules, they come together as the clusters of the nanostructured materials. Each of these bright spot, it represents a quartet, 4 of those functionalized clusters, which is about 6 nanometer in size. And they are separated by 12 nanometers. This is atomic force microscopic view of that one. Again, a new breed of nanostructured materials with well-defined properties resolved at the atomic level, and you can change them. So this is an important feat that you can change the properties. This is a new class of single molecular magnet materials where you can do a lot of activities, especially in the imaging area. This is an active area being explored in my lab. These are molecular magnets, they're soluble, they're benign. All the inorganic chemistry is basically enveloped under an organic core, and they are ready to be linked to the biological system. This is yet another area, which is just one slide. You can use them actually to produce a new class of colloids. This is the colloidal translucent material. Indeed, their properties, Dr. LaSalle Swenson, he defended his PhD thesis exactly on these new colloids, which I just want to show that this is a new horizon emerging. What they can do is still we are investigating, but their electro properties, the electrochemical properties is just very interesting and very exciting features. They are electrochemical materials, but now in the colloids form. Returning back to the original theme, that removal of these, the new materials are catalysts, heterogeneous catalysts for removal of NOx gases. This is a slide which has got a wealth of information into, but I just want to show you that these zeolite type of materials made of these clusters could be used as a denox catalyst. Here is the NOx removal. In the best world, you can decompose nitrogen oxide into N2 and O2 by using a reductant. We did not use ammonia, but used hydrocarbons. Just hydrocarbon is the reducing agent. What you see at a certain temperature, here about at 350 to 390, depending on which catalyst, it takes up, this is called induction time. And then it reaches to this one. This is almost quantitative removal of NOx gases. What is happening? The NO is going into N2. This is very desirable thing. This has to go into N2. Now, hydrocarbon, which you are using, like propane, this is a reducing agent. You cannot make carbon monoxide. So the key is that you have to hold your breath, that it is not, because you cannot solve one problem, create another one. So look at this, where it is going. Essentially, hydrocarbons are going into water and CO2. And you can see the carbon monoxide line, this is dark maroon, this is zero. There's no carbon monoxide. So NO is going into N2, which is green, which is very, very welcome thing. And rest, everything carbon is going into carbon dioxide, which is acceptable. It is not carbon monoxide. So this is something which are saying is extremely promising. So I'm not saying that I have solved the problem of now, but this new class of materials are saying this is extremely important. I will switch on to show you sensors. So they are the same materials are NOx sensor. So it took us time because we are not device makers, but we developed our own sensor devices. So this is the technology of stamping and etching and curing. It took us some time actually, but eventually you can have a thin film of the material in between the two electrodes, and this is the device. This is the new semiconducting devices made up of our own material, everything done in my lab, okay? So this is something what you happen that this we put in a sensor testing device, our own in-house, everything. It took us some time because we are molecule makers. We are not engineers. It took us some time. It's one PhD thesis of Summer Ash, who is a professor in a college now in the Chicagoland. So this is something you can see. This was just something unbelieving. Sometime when I saw this plot, this is the sensor response. So nitrogen oxide, when you put through these devices, you see that this is from 5 ppm to 200 ppm. This is all spectrum. As you turn on this, you see this sensor, right? This is the response. When you turn off the gas, it quickly comes back. This is called response recovery time. This is less than a minute, which is a dream. Another thing is that sensors generally do not recover 100%. Even 70% is good. They are almost coming to the baseline. And at every concentration. So this is something which is absolutely gorgeous from these materials. That more important, these sensors act as room temperature. Nothing like this has ever been known. All are at 400, 500 degrees. So this is just one shot, you solve this problem. Furthermore, you see that as you change these linkers with the catalytic side from cadmium to zinc to this one, it is specific. So that means you can fine tune this sensor at the molecular level. So this is, so what I have shown you, it is room temperature sensors for the first time. The good sensitivity, rapid response and recovery time, reversible and completely reproducible, and long-term. So these sensors have been tested for 6 months of time, and they are perfectly okay. One thing which is very kind of always the sensor community is at toes is because so it is cross sensitivity that they should be only specific. So you can see these sensors, they are more performing to nitrogen and nitrogen oxide and almost no response. This is called cross sensitivity. And this has been done from room temperature to 175. So that is still very good, that they are responsive to NOx gas. Another concern for the community is essentially in the area. So I hope that I made this point. This is cross sensitivity. So this is responsive to, this is one class of materials, okay? At 125, you can see this is sensitive to NOx gases. And almost, these are the real world in this thing. Carbon monoxide, sulfur oxide, hydrocarbons are present, but almost there's, so this is the real thing. At higher temperature, again, they remain sensitive to the NOx gases and less to this. So cross sensitivity, even at room temperature and to higher temperature, they are the same. One thing one has to be aware of, that humidity kills sensors. Sensing community knows that, okay? So sensor, and in the real world, there is always humidity. So you are having incredible material, but the moment this is the water, they die. And that, of course, is no, you can use only once. This is something, so this was our concern. So we simulated humidity in the lab. So what humidity you could have? I mean, could be 85%. You have to be almost living in the ocean to get that humidity. And you can see that 5% to 85% humidity. You see the sensors, they are all stable. Okay, this is all. So the sensitivity, it does not change at all. Okay, so from again the nitrogen gas concentration from nitric oxide from 25 to 250, and you can see the relative humidity. So it is almost, you can dip the sensor in water and this is stable. So that is again, so what I have shown to you, it's a new class of materials based on molecular building block approach from bottom up. And we have created a new generation of transistor metal oxide materials, which are embedded neatly with catalytic sites, which we can change. And by changing this, I can change the properties. By changing the properties at the molecular level, you can make molecular magnets, you can make as a DeNOx catalyst, oxidative dehydrogenation catalyst, are sensor materials. And these are sensor materials, they are rock solid because they are made up of transistor metal oxide. They are metal oxide, nothing happens to them. And they operate fundamentally at room temperature, which is extremely good sign. And they survive the humidity onslaught. They are okay with up to 85%. And they work at all range of NOx concentration, all range. And they having no cross sensitivity with other environmental gases because the sensor had to be used. So I think that if I was allowed to share one slide, I will do this. This summarizes everything. So we have shown you from molecular building block, from known inexpensive, environmentally benign metal oxide clusters, we can create nanostructured materials. And these things can be made just out of the shelf chemicals. You can buy it, just do it in the water, 90%. Then you can make them nanostructured, well-defined zeolitic materials. These materials, this is one class, there are many. These materials are DeNOx catalysts, they are NOx sensors, and oxidative dehydrogenation catalysts. So in this one slide, there are 4 PhD theses, by the way. Okay, and that is the work which I have presented today. I hope that I was able to show you that the first class chemistry could be done inexpensively at relatively no cost to environment, but it requires a little effort. And I am a great fan that the direction of materials design and development should be in this way, which is inexpensive, environmentally benign, and still you can produce material, because we cannot solve one problem and create 2 others down the line. This is the direction to go, and this is what it is. So with that, I think that I have almost reached my allotted time. And I would like to thank once again the organizers for arranging this beautiful forum and finding a way to still meet and not to cancel the program, which is a smart move. And Mr. Chairman, thank you very much indeed for allowing me to speak with your audience and with you. If you want to find out that where is thank you in Turkish, right? So thank you. Assalamu alaikum. Peace be upon you.
Teşekkür ederim. In Turkish, teşekkür ederim.
Shukran. Good. Thank you.
Thank you very much for this very fruitful and very interesting presentation, Professor. And I think Dr. Atesh also want to thank you.
Yeah, Dr. İshak Khan, dear Professor, my hocam, thank you very much for your attendance. You every time support us like other professor. This is very good presentation, and thank you. See you again.
Thank you very much indeed. It's a pleasure. I would like to see you in Turkey and next time.
Inshallah, after pandemic, all of you, Hüseyin Şehitoğlu, Joshua, and all other professor, I will invite you to Turkey, and after conference and activity, we visit some historical and sightseeing together.
We look forward to that. Thank you.
Thank you.
Thank you very much indeed.
Thank you very much.
Bye-bye now.
Bye-bye.
Have a nice day. And the next speaker is Joshua Robinson, who is, sorry, Dr. Atesh.
We will play his video.
Yeah,
Then
I prepare a video and I share my screen now. Okay. But okay, I think you can see it here. And Joshua Robinson is the Director of User Programs, Two-Dimensional Crystal Consult in MIT, Professor of Materials Science and Engineering in Penn State University, Associate Director of Center for Two-Dimensional and Layered Materials, and also co-director of the National Science Foundation Industry University Cooperative Research Centers and Program Center for Automatically Thin Multifunctional Coatings. Dr. Robinson's interest area are the synthesis of two-dimensional materials, integration of two-dimensional materials with the three-dimensional materials, and the transport, sensing, and functionalization of the two-dimensional materials. And since Robinson cannot attend to this presentation, I want to play his video now.
My name is Joshua Robinson, and today I'm going to be speaking to you from State College, Pennsylvania in the United States, courtesy of COVID-19. I'm going to talk about graphene-enabled quantum materials. Before moving forward, I just want to show what really matters, and that is the students in the research group here going from 2019 and some of our students in safety, and our 2020 COVID version of group meetings and happy hours. Of course, there's funding as well, and lots of collaboration that have allowed us to achieve what we want to be able to do scientifically. So atomically thin materials, these are typically defined as materials with in-plane covalent bonding and out-of-plane van der Waals bonding, so that they can easily be mechanically exfoliated. And there's a wide range of properties for these systems, ranging from insulators all the way to semi-metals and metals in these systems. There's definitely superconducting properties, as well as MOS2 and HBM, which are semiconductors and insulators. We've written extensively on 2D semiconductors. One of the latest ones that came out just last year was a roadmap to electron grade 2D materials. And this really focused on the synthesis, heterostructures, defects, doping, and theory, all towards applications in the electronics industry. And as part of the work at Penn State, we have the 2D Crystal Consortium. It's an NSF materials platform, innovation platform, and focuses on a very wide variety of synthesis of 2D materials and looking at the synthesis science of 2D materials. And is open for user proposals, and have a variety of outreach mechanisms. You can look at mif.psu.edu to learn more about that process. So within my own group, we do a significant amount of work in 2D materials. We started off with graphene, and then moved into the chalcogenides. These are the chalcogenides here, selenium, tellurium, sulfur, and transition metal dichalcogenides, primarily looking at molybdenum and tungsten, and doping with niobium, rhenium, and now iron, as well as 2D, 3D heterostructures and half van der Waals materials, which we'll talk about a little bit later. And a lot of the work that we've done for these TMDs is really utilizing this solid source CVD or powder-based CVD and metal organic CVD. Today, what I want to talk about is a very old topic and that is metals, a 7,000-year-old topic. So we've learned a lot in the past on this, and there's still a lot to learn moving forward. And this is because we can shrink them just to a few atoms thick. And if you do that, one of the interesting things is that you can get very unique properties: topologic behavior, superconductivity, ferromagnetism, nonlinear, interesting nonlinear optical properties. So there's this whole range of material systems that we can now explore, that we've been exploring for millennia. The problem is when you have a thin metal film, generally what happens is it oxidizes quite rapidly. As soon as it's exposed to ambient, within a few seconds, you can get a nanometers worth of oxide. Or if you try to grow something on top of it, on top of these metals, you quite often will get significant reaction at the interface. So this generally limits these types of metals, or thin film metals, other than maybe gold, to UHV conditions for deposition or very specialized capping techniques. And so this really kind of limits their ability to be utilized.
Professor Irfan, I do not hear the video. Perhaps you need to unmute. So sorry, everyone. It sounds like we are having trouble with the volume in the video. So I'm going to, I guess, attempt to speak through this while we do it. I was just afraid that we would not have a proper video link for me to be able to share. That's why we're going through the process of running the video, but it sounds like we've got some issues there as well. So the way that we're doing our confinement heteroepitaxy, and matter of fact, I will go ahead and share my screen so that we can get back on track, is to first start off with silicon carbide. What we do is sublime silicon from the silicon carbide at 1800 C. that forms carbon on the surface, which rearranges to then create a buffer layer at that interface. It's a very high energy interface. And in fact, when you do cross-sectional TEM, what you see are the atoms shown here, which are carbon atoms, and our buffer layer, which again is partially covalently bound to the silicon carbide substrate. And once we get to the formation of this, because it's very high energy, it wants to be passivated. So we open up windows to the interface using a plasma reaction to create these windows at the silicon carbide. And then we evaporate metal onto that surface. We do that evaporation of the metal for at approximately 800 C for the substrate temperature. And when we do that, the metal hits the graphene. Where it interacts with these graphene windows, it then intercalates into the center of it. So when you do it properly, what we find then is that we can create these two-dimensional metals, and these 2D metals, which happen to be gallium, indium, tin, and silver here, in fact, demonstrate that we are able to create these 2D metals at this interface using this process. And thermodynamically, in fact, what we find is that they are most stable at just a few atoms thick. For the case of gallium, 1, 2, and 3 atoms are most stable when you look at the energy versus chemical potential in these systems. And in fact, you can do this same DFT modeling for a wide variety of the periodic table. And it suggests that as you get to larger atoms, for instance, going from gallium to indium to tin, we go to a thinner and thinner layer because of compressive epitaxial compression. The defects in this are quite important in creating these windows for the metals to come into the interface. In fact, when you do not utilize the defects or this defect engineering step, what we find is we only get a small amount of creation of this 2D metal, which is shown here in SEM and Auger spectroscopy chemically. And in fact, when you do have the defect engineering step, you can get up to 100% intercalation, which is critically important whenever we're trying to get uniform device properties or material properties across the interface. The defects that are typically most used or most effective happen to be carbon-oxygen bonds in these systems. So you can see by the binding energy in the material systems, use my laser here. If we do not have carbon-oxygen bonding and we had tried to get a metal to go through these graphene defects, the binding energy is actually quite high, indicating that it's going to simply bond along the edge and you're just going to create these depositions on the surface. However, when we functionalize it with carbon and carbon-oxygen bonding, that binding energy is significantly reduced. And it allows us to do what we would think of as a catch and release process, where the metal comes into close contact with the defects due to this attraction, but it's not so strong that it can't be released into the interface of the material. And in fact, one of the things that we've modeled with molecular dynamics is the carbon-oxygen and carbon double bond and single bonds, and the binding energy increases as we go to larger and larger defects, where we actually find that penta and hexa seem to be optimal size defects in these materials. Interestingly enough, there is a significant amount of evolution of the defects as you go through this process. So I'm showing XPS here in the center and Raman spectroscopy over here on the right. XPS tells us the type of bonding that is occurring. So we have our carbon bonding in our graphene layer. We have a carbon bonding in silicon carbide, as well as carbon bonding in this buffer layer, the region that is that's in between graphene and the silicon carbide. So XPS can really tell us what's going on at this with the chemical environment. Raman spectroscopy can tell us about the defect generation or defect formation in the materials, where this D peak here indicates, tells us whether or not we have a large density of defects or not. And you can see in the as-grown cases, peak is quite small compared to the other two that are symmetry allowed in graphene. Interestingly, when we do our plasma treatment of the graphene, which we would expect to create defects in the material, in fact, we do see that, we get a large amount of carbon-oxygen bonding, which shows up in XPS, as well as a very large D peak in our Raman spectroscopy, much larger than the G peak, indicating again that there's a very high density of defects. But the most interesting part actually turns out that once we do this metal intercalation, once we evaporate metal onto the surface and it goes into that interface, what we find is, in fact, that we get a complete removal of the buffer layer, as well as this carbon-oxygen bonding. You can see they've both gone away, and there's this splitting that occurs. And we see that our D peak, or the defects in this material, have now been healed. It's not anything miraculous. We do not have divine intervention. But what we believe is going on is that we are catalytically regrowing the graphene during this process. And this catalytic regrowth ultimately leads to an ability for us to be able to see or directly measure a significantly lower defect density. And interestingly enough, one of the other things that enables us to understand that we have healed the graphene defects is the fact that when you create these 2D metals, which we would fully expect to be completely oxidized in air, they remain stable up to 9 months. So these are metals that are only a few atoms thick, capped by graphene, and therefore this graphene acts as a nice diffusion barrier for the environment. And in fact, you can see you don't need to know a whole lot about XPS, but you can see that all of the spectra here have not changed much over the course of 8 or 9 months. And that means then that we can spend extra time characterizing these materials and understanding their unique properties. So when we do cross-sectional TEM, in fact, what we see is that the metal bonding here is kind of an ABC stacking for these metals. And the first atomic layer of the metal is typically lined up with silicon on the silicon carbide. And taking this in combination with low energy electron diffraction and feeding that into our DFT theory colleagues tells us that these ultra thin metals take the structure of a 1-1-1 plane of an FCC structure. So we heard earlier about some metallurgy in terms of twinning and split planes, etc. This is the 1-1-1 plane of one of those metallic structures. But there's a little bit of additional interest in this, in that when these are bonded, and you can see this in the TEM here in layers 1, 2, and 3, there's actually the atoms are separated. They're not equal, the distance. And what that means then is that their electronic properties are not equal as a function of position. And you can see that in the DFT here. We're looking at the electron density of the material, silicon carbide down here at the bottom, which is relatively uniform density as you go through the layers. But once you get into the metal, that density changes. And it goes from a covalent into a metallic bonding in an order of a few angstroms. This leads to some interesting phenomena, one of which is that when you look at the structural signatures of these using Raman spectroscopy, regardless of what these metals are, they have unique fingerprints, so that we can directly then measure what these unique fingerprints are in the material system. And in addition to that, when we're alloying these elements together, say a metal alloy here, the Raman signature, in fact, changes as well, telling us that the atoms in our material, the atom vibrations, the mechanical properties are changing. And you can directly measure this in our low frequency spectrum, where we get this linear correlation in the phonon vibrations as a function of alloy composition. This also enables us to be able to use techniques like Raman spectroscopy to identify different phases in the material, whether it's thick or thin, because they have unique signatures in the Raman spectroscopy. Where our thin gallium, or basically two atomic layers of gallium, have additional peaks identified here in these purple dashes, compared to something that's thicker, which is multi-layer, which has the peaks here in the red. Both of which, though, also have this peak here in the gray. The same is for silver. You can distinguish layer thicknesses in here in terms of whether it's thin or thick material systems, because phonons become more complicated and intermixing as they go forward. So one of the things that we find then is that as we go through and we're identifying this, the properties, in fact, is that we have covalent bonding in the material as well as metallic bonding as we move up through this, and then van der Waals. So over the course of about 1 nanometer or so, we see 3 different types of bonding, which is highly unusual in a metal. And it leads us to being able to call this a 2D polar metal, because the bonding in this is quite polar. And that leads to ultimately, again, very unique properties. The first of which I'll talk about is the optical properties, or the optoelectronic resonances in these systems. So it turns out when you look at plasmon resonances or electronic resonances, you see that there's scattering in the system. And we get these peaks in the visible and near IR, suggesting, in fact, that we get some interesting light matter interactions in these systems. And in addition to that, the coherence times, or the lifetimes of these 2D metals, these plasmons in the system, are significantly longer than what you would expect in gold. Or silver, on the order of 2 to 3 times longer. And that then means, from an optical standpoint, is that we may be able to use these materials to enhance optical interactions that we would typically use in plasmonic nanorods or nanoboxes. And the primary thing that we're interested in are things like second harmonic generation. So this is used quite often in lasers as we go from, say, for instance, a red laser to a green laser. What happens is they use crystals in these lasers so that it combines 2 red photons together to form 1 green photon. And so that's known as second harmonic generation, or where we double the frequency in these materials. That's all based on this nonlinear susceptibility in the polarization term. So this chi2 value is very important to tell us how well can we do frequency doubling in optics. So normal chi2 values that you would find in the literature and in current state of the art are on the order of maximum 0.1 nanometer per volt, which is lithium niobate. But when you go to 2D materials, in fact, what you see is that you can enhance this value so that we get stronger second harmonic generation. But in fact, when you go to these 2D metals, which have this very strange bonding from covalent to metallic to van der Waals, you get an even further enhancement. So we're on the order of about 100 to 1,000 times larger chi2 values than what is in the literature right now. And in fact, this leads to our ability to do second harmonic generation that is quite strong compared to what is in the current state of the art. And in fact, when we pump it with 1.5 eV photons, so red photons, they plasmonically combine to create 3.1 EV. So we're really interested in this peak here at the 3.1 EV. If you look at gold nanorods, which is the current state of the art, they have a peak shown here with a large background. And in fact, when we look at our 2D metals, we see a significant enhancement, about an order of magnitude enhancement in the signal. We also see a 10 to 50 X reduction in this background scattering. So that means our signal is going to be much more clean. And that ultimately then means we can utilize these systems for laser applications or surface plasmonic applications. And one of the reasons that we are finding that we can use these is because the graphene that sits on top of these 2D metals quenches this non-coherent processes down here. So that actually is able to filter out, just by the fact that it's there, all of these unwanted signals. And the fact that these 2D metals have this unique bonding in the center means that they've got a very interesting dielectric properties or dielectric function, where we get these epsilon near zero peaks or crossings. So that means that our dielectric constant goes across zero, and the closer it is to zero, specifically in these regions that have been highlighted, the stronger the light interacts with the material and the more energy transfer you can get. And just so happens that we were pumping with 1.5 eV photons, which is very close to this 0 point in our materials. So we're getting very strong interaction, and that ultimately is what leads to this very large peak. And the reason, again, that we're interested in these is because of some things like plasmonic metasurfaces. So this is an application of these materials that we're currently striving for. And that is because in these 2D plasmonic systems or metasurfaces, you can create extreme light matter interactions for optical filters, mirrors, waveguides, etc. All that can be directed towards optical computing, quantum computing, surface, ultra thin or atomically thin mirrors for a variety of applications. So the second part of this we really want to focus on is quantum, because that's in the title, and it's been around for quite a long time. But what I'm showing here is the Gartner hype cycle for 2018, where expectations is on the y-axis, time is on the x-axis. And we have several different regions of this, where we have our innovation trigger. So that's where a lot of the science and research begins. And then this peak of inflated expectations, followed by the trough of disillusionment, slope of enlightenment, and plateau of productivity. And we all hope to eventually get over here to the plateau of productivity, but quite often from essentially the peak of inflated expectations to somewhere upwards of the slope of enlightenment is what we would think of as the technology valley of death. So if you look closely at this Gartner hype cycle, you see quantum computing is going up in this, and it's on its way to the top of our peak of inflated expectations. And this is readily visible by just seeing how the U.S. has now put about $1 billion into quantum, as well as the quantum flagship in Europe with €1 billion over the course of 10 years. So this is really a big deal, and this is in addition to a variety of strategic efforts in Japan and China, as well as various other developed countries. But the thing that's really interesting to me in this whole thing is the fact that it really is a materials playground. We've got semiconductors, superconductors, magnets, single photon emitters. There's a variety of things that we can do in the materials aspect to be able to enable next generation quantum computing. And one of the most specific examples, or a specific example, is some of the proposals that have come out of IBM for topological quantum computers. Now, these are special types of computers that indicate, or that are ideally inherent fault tolerant. And what that means then is that we can create this computer or the integrated circuits as part of this computer, the chip, the transistors, if you will, in terms of traditional thinking. And we don't have to worry so much about defects because of the way that the physics is that they're protected from those defects. Now, this is a very simple drawing from IBM based on what their proposal it was for a topological quantum computer. There are semiconductors, superconductors, topological insulators that make up this. And at the intersection of the semiconductor and the topological superconductor, we get these mirror on zero modes, which is where most of the communication occurs for the operation of this. Now, there's been many years, many decades of semiconductor fabrication and research. So we don't really have to worry too much about the semiconductor part of it. But the big question is do we have topological superconductors and traditional superconductors that are amenable to integration into this thin film process that is typically utilized in the semiconductor industry? So if we take a look at atomically thin superconductors, ultimately what we see then is that, from this nice review in 2016, is we can get a wide variety of highly crystalline, high quality, ultra thin superconductors. These are on the order of about a nanometer thick. And there's some traditional 2D materials in there as well as elements. Quite often, they either are going to rapidly oxidize or they require very heavy doping, so that aren't necessarily technologically relevant. The key, though, is, like I was talking about earlier, is that there is gallium in this. And I was just showing you that we can make stable gallium that is stable over the course of many months, as well as some processing. And in fact, then what we did was we took a look at our 2D gallium and saw that we do get superconductivity in these materials. In fact, it's superconducting at about 4 Kelvin, which may not seem like very high, but this turns out to be enhancement of about 400% compared to traditional gallium. So traditional bulk gallium has a superconductivity temperature of about 1 Kelvin. And the reason we're interested in this is because if we can increase this superconducting transition temperature, then we don't have to go to as high level cooling as we would need for current technology, which requires on the order of 100 millikelvin or so. So this being a material science, advanced material science conference, we need to talk a little bit about the material science of creating these systems. And it turns out that the substrate plays a very critical role in this. So this is atomic resolution TEM of the silicon carbide substrate, which is just under here, and our 2D metal. And then there's a graphene layer on top. And what we generally see are two types of surface structures, specifically from the silicon carbide, and that is regions where we have very small atomic steps in the silicon carbide, which can still somewhat disrupt the metal, or we have these large terrace steps on the order of 5 to 10 nanometers. If we look at superconductivity as a function of direction on the surface, what we find is in these regions with the small steps or samples, substrates with small steps shown here by the AFM, we're still able to achieve superconductivity with relative ease. We do see that there's some disorder based on the shape of this curve. There's a little extra shoulder here. But when we look at the larger stepped samples, in fact, we can't actually get all the way down to 0 or superconductivity measurements. And even when we're going perpendicular to the step, so when we're looking at superconductivity over this step, which makes sense because it's actually breaking the metal continuity quite readily. So where is this superconductivity coming from? So there's claims, there's twisted bilayer graphene, which claims that it has superconductivity based on the layer-layer interaction. And there's also heavily doped graphene, which can be superconducting. So what I'm showing here are angle resolved photoelectron spectroscopy maps of energy versus momentum of electrons. There's not based on the previous talks that we've been listening to today, this may be somewhat foreign, but essentially what we're doing is mapping out the energy and direction of electrons in our material as a function of the crystal lattice. And in fact, what we find is when we look at the graphene curves, or the energy and momentum of the electrons, is that the doping in the graphene is actually quite low. It's about 100 times too low for it to be superconducting. And that's just shown by the ARPES measurements here. And the other part of that is that if we look at this nice curved circle here at the Fermi surface of the gallium, we have a nearly free electron Fermi surface, which with electron velocities greater than that of graphene. And this is specifically for the gallium, which means then that it has it's the right flavor of material to have superconductivity in and of itself. The other thing that we were interested in understanding is, why is our superconductivity actually higher? The temperature is higher than what you would see in a normal superconducting metal like gallium, because we were expecting superconductivity on the order of about 1 Kelvin. You know, these are really, really low temperatures, which may not seem realistic. But when you go to these 2D materials, or these 2D metals, we actually see that the temperature goes up. And it turns out that it's directly related to the density of states, or the density of states near the Fermi level in these materials. And that's because superconductivity directly correlates with electron density of states at the Fermi level. And if for traditional materials, what you see, or the traditional alpha gallium, you see that it actually has a lower density of states than these 2 and 3 layer gallium on silicon carbide, which is what we've developed. So that means then that our transition temperature is going to be significantly higher. And in fact, we also get very strong electron phonon coupling between the gallium, or in the gallium layers, as well as some at the gallium silicon carbide interface, which again is a key indicator that the superconductivity is coming from the metal itself. So we now have a thin film, or an atomically thin superconductor, that we can utilize at nominally liquid helium temperatures, which turns out to be about 100 times higher than what others have been able to do for the same. The question then is a topological superconductor. So topological superconductors are like unicorns. They're quite elusive. And in fact, finding a single material that is a topological superconductor is essentially impossible. There's very few materials out there that actually could claim to have this quality. So what we are looking at then is, can we create artificial quantum layers that will enable connecting a topological insulator or a semiconductor with a superconductor? So it's a heterostructure in that sense. Generally, what is done in the state of the art now is, in fact, just depositing a superconductor on top of a semiconductor. And this is most well known for putting aluminum on indium arsenide nanowires or indium gallium arsenide semiconductors, shown here. These are two typical examples that are pulled from the literature. And this with the band structure shown here in this. Now, what you see though, when you put a superconductor on top of a semiconductor, you get these little gaps in the band structure. These are known as exchange gaps, and these are critical for creation of topological superconductivity. The problem is these little gaps in energy that are created by making this heterostructure that you see here. It's actually very small. It's only 10 millieV, which means then that these systems have to run at about 100 millikelvin. So this is where I get the hundreds of times higher from what we were originally seeing. And the reason is because of the semiconductor. Indium gallium arsenide has strong spin orbit coupling, but the combination of aluminum with these being a low temperature superconductor leads to this exchange gap that's very, very fragile. So we need to improve this so that it becomes more robust. And in fact, this is something that we believe we can do by using a material system known as topological insulators. So they are conductive on the surface, but insulating in the bulk. And so you can think of this, so there's vacuum here, here's the surface. So we have spin splitting, spin up, spin down, it's conductive, but in the center of it, it acts like an insulator. This was an important enough finding that it was awarded the Nobel Prize in Physics in 2016 for a lot of the theory done by these three gentlemen back in the 70s and 80s, predicting that these materials would exist. And in fact, they do. There's a wide variety of them now. There's dozens of them. The ones that we are primarily focused on are the ones shown here. In the bismuth selenide or bismuth antimony telluride families. They have their band gaps on the order of 0.3 EV, a little bit less. And the reason that we care about this is because if the gap of the TI is greater than 100 millielectron volts, then that's actually quite significantly larger than the gap that I was just showing, which was 10 millielectron volts for indium arsenide. So it provides us with this route then to imagine putting superconductors in combination with topological insulators instead of a semiconductor as a way to create a more robust topological superconductor, which again is key for this the topological quantum computer. So the process by which we imagined this was utilizing our confinement heteroepitaxy, which is CHET, which is the one we're creating our 2D metals with, inserting that between at the graphene silicon carbide interface, which is what I've talked about in the past, or what I just, a few slides back, and then utilizing molecular beam epitaxy to deposit the insulator on top. The graphene here should provide an inert interface so that our superconductor, which is our metals here, can couple with our topological insulator deposited by the MBE. So that's what we've begun doing. We're now looking at this in a growing bismuth antimony telluride topological insulator on top of our 2D metal. This is just cross-sectional TEM with EDS signal showing that we don't get intermixing. And in fact, if you do zoom in here and look at the actual atomic structure, you can see we have our gallium, silicon carbide, epitaxial graphene, or our graphene, and our topological insulator. It's a nice atomic structure here, which is critical for us to be able to get coupling between our superconductor and our topological insulator. So then the question is okay, we've grown on this. We've created this heterostructure. Do our little Lego pieces actually still superconduct, and is it still a topological insulator? And so looking at ARPES again, what we see is the fact that there's a V shape here in our ARPES signal indicates to us that we have surface conductivity on our bismuth antimony telluride. And that means then that it is still a topological insulator. And if we look at resistance versus temperature for our gallium metal or our 2D metal, in fact, we see that it still drops at the very similar temperature, about 4 Kelvin, with our bismuth telluride in this particular case grown on top of it. The resistance does increase at higher temperatures, but we still get superconductivity performance at these lower temperatures. So our Lego pieces still act as they should, which indicates that we do potentially have the makings of our topological superconductor. And we worked with our theory friends, colleagues, to theoretically identify, will superconductivity in gallium be translated into the topological insulator and thereby create a topological superconductor? This is a big DFT mess over here on the right. But the key takeaways here, is that our graphene Dirac point falls within the band gap of our bismuth antimony telluride. And this actually should be telluride instead of selenide here. But the reason that is important, the reason that it falls in the band gap means that it's going to essentially be invisible then to the bismuth antimony telluride, which is key for when we want to get proximity effects from the gallium into our TI, because we cannot have interruptions in the proximity effect in that due to the graphene. So experimentally, we've been able to put the Legos together, and theoretically, we've identified that we should be able to create a topological superconductor in this system. So the question is do we really have one? My answer is you're going to have to invite me back next year to talk about it, because the measurements are currently ongoing with colleagues in the physics department to verify it. We do have some very promising initial results in this, suggesting that it is and it does exist. However, we are not confident enough to fully show that in public yet. So in summary, I do apologize for the initial technical issues that we were having, but I think hopefully everybody can still hear me. I talked a bit about confinement heteroepitaxy, where we utilize graphene as a hermetic seal to create 2D metals that have unique bonding properties. And in addition to that, these unique bonding properties lead to enhanced optical properties in these material systems compared to their traditional 3D materials. And it's also enhanced the superconductivity and the electronic properties of 2D systems compared to their 3D counterparts. So going to atomically thin really has opened up a brand new world in these 2D metals that we had not initially expected. A lot of this was recently published in Nature Materials for the superconductivity. The optical properties is on archive, and then we have a recent review in nanoscale on this. And we truly do think that we're only at the tip of the iceberg. We think there's a lot more to come because we have essentially the periodic table to explore in these systems. And we have this Lego combination of different 2D metal systems that can be superconducting or ferromagnetic, and in addition to combining materials on top. So one more time, I'd like to just point out what is most important to us is the folks that are doing the science. Here's a 2019 before COVID, and then of course now COVID, we're all doing our own individual Zoom in. I'd like to thank the funding support and the collaborators on this, as well as Professor Atesh for the invitation. Hopefully I've been able to contribute to this, and I am happy to take questions.
Thank you very much for your presentation.
Hopefully it wasn't too disrupted by the various things that are going on.
There may be some difficulties in technical point of view, but I think we solve it. But we cannot expect next year for your answer. Dr. Atesh, do you want to say something?
Yeah, I am free. There is nobody here. Professor Joshua, I am very happy to meet you. Thank you very much to join us and support us. We are happy you, and next time we hope to host you in Turkey, both conferences and some cultural and touristic activity together. As you know, Turkey is a very great country, not only their good things, but also their not only scientific side, but also Turkish seaside, tourism, and so on. So thank you very much. We are very happy to listen to you. Very nice presentation.
Thank you. I appreciate the time.
Thank you for your nice and very fruitful presentation, Dr. Robinson. Thank you.
Thank you.
Have a nice day. Okay. Now, our next speaker is the Professor Dr. Münir Naifi. Professor Münir Naifi received his bachelor's and master's degrees from the American University of Beirut in 1968, and he earned a PhD in physics from Stanford University in 1974. He served as postdoctoral fellow and research physicist at Oak Ridge National Laboratory in 1974 to 1977, and as a lecturer at Yale University in 1977. And before joining the physical faculty at the University of Illinois in 1978, his interest area are the search for quantum chaos, writing with atoms, preparation and characterization of porous silicon, and atomic electrons. Following his arrival at the University of Illinois, Professor Nafi developed an active experimental program to study the multiphoton nonlinear dissociation of molecules as means to enhance dissociation selectivity. He was also the first physicist to examine the behavior of hydrogen molecules in intense laser fields, and his seminal work in this area initiated a whole new area of research in molecular column explosions. Now, Dr. Nafi.
Dr. Irfan, I think, as well I understood, he couldn't connect now. Probably we can pause a little bit, or we can pass the other presenter, other speaker, if they ready. I am checking, and he couldn't join.
Yes, but we do not have the Dr. Naif video. We did not present the video, so I want to present the Dr. Okyay, Assistant Professor of Ali Kemal Okyay.
He couldn't join now.
We start with the
other one.
Yeah.
I will check.
I want to invite the next speaker. If Dr. Naif can combine, then we can take after that. Okay.
Yeah.
Now I want to invite the Assistant Professor of Ali Kemal Okyay. He is the Assistant Professor of Electrical and Electronic Engineering in Bilkent University.
He was. Now he is in US from Okyay Technology, and he is a visitor researcher in Stanford now.
But his web page does not change.
Probably we can pass to Bilgehan Barış Öner if their presentation is ready.
We have his presentation. Let me
or we can make some pause, 10 minutes.
No, it doesn't necessarily. Please, I try to start his video.
You can start with, yeah, right.
Hello everyone, I am Bilgehan Barış Öner from Gazi University Department of Physics, which is located in Ankara, Turkey. My presentation will be about light extraction efficiency enhancement of indium gallium nitride near ultraviolet LEDs by genetic algorithm. Now, please let me begin by the main content of this presentation. The first section will be a brief introduction, actually the motivation and the concept of our study. Later on, I will introduce the main schematics of indium gallium nitride-based light-emitting devices. The next slides will actually be a detailed motivation of the study. Also, the material and methods will be given at the same time. We have used an optimization algorithm on efficiency calculations, which will be explained in the section of optimization method, and then corresponding results will be shown. A discussion will be given, and then finally, I will conclude my presentation. The history of light-emitting diodes have begun almost 70 years ago by William Shockley. The spectrum of LEDs were within infrared spectrum back then until the invention of the first visible light-emitting diode, which was proposed by Nicolas in 1962. Later on, the semiconductor technology has developed greatly such that LEDs have become available even in deep ultraviolet regions these days. The ultraviolet light-emitting diodes play an important role for many varieties of usage in semiconductor light technology, such as high-resolution data recording, white light illumination, combined fluorescence ultraviolet LED systems, and some other application areas in medicine and biochemistry. However, ultraviolet LEDs efficiencies diminish severely as the operating frequency increases, such that efficiency improvement of these devices is still a popular topic in scientific researches. As well known, semiconductor technology is based on p-n junctions, which can be evolved to pin junction by inserting usually an undoped intermediate region. Therefore, light generation can be produced by radiative recombination mechanisms. And this mechanism Hello everyone, I am Bilgehan Barışoner from Gazi University Department of Physics, which is located in Ankara, Turkey. My presentation will be about light extraction efficiency enhancement of indium gallium nitride near ultraviolet LEDs by genetic algorithm. Now, please let me begin by the main content of this presentation. The first section will be a brief introduction, actually the motivation and the concept of our study. Later on, I will introduce the main schematics of indium gallium nitride-based light-emitting devices. The next slides will actually be a detailed motivation of the study. Also, the material and methods will be given at the same time. We have used an optimization algorithm on efficiency calculations, which will be explained in the section of optimization method, and then corresponding results will be shown. A discussion will be given, and then finally, I will conclude my presentation. The history of light-emitting diodes have begun almost 70 years ago by William Shockley. The spectrum of LEDs were within infrared spectrum back then until the invention of the first visible light-emitting diode, which was proposed by Nicolas in 1962. Later on, the semiconductor technology has developed greatly such that LEDs have become available even in deep ultraviolet regions these days. The ultraviolet light-emitting diodes play an important role for many varieties of usage in semiconductor light technology, such as high-resolution data recording, white light illumination, combined fluorescence ultraviolet LED systems, and some other application areas in medicine and biochemistry. However, ultraviolet LEDs efficiencies diminish severely as the operating frequency increases, such that efficiency improvement of these devices is still a popular topic in scientific researches. As well known, semiconductor technology is based on p-n junctions, which can be evolved to pin junction by inserting usually an undoped intermediate region. Therefore, light generation can be produced by radiative recombination mechanisms. And this mechanism should be supported by a substrate due to fabrication issues. This brings a lattice matching conflict between the substrate and the junction. Thus, an intermediate buffer layer is generally inevitable. Here, a problem arises on all standard LED designs such that emitted electromagnetic waves within the active region are not guided in general. This causes light to have arbitrary propagation directions. In this manner, we propose one-dimensional photoelectric crystals, namely distributed Bragg reflectors, to be utilized in the design to enhance the light extraction efficiency. Also, an electron blocking layer is strictly required to balance the current. And finally, we propose to reshape the surface by gratings to enhance the light output ratio. These gratings are supposed to serve the same role as an anti-reflection coating without a need of additional material. The efficiency of an optoelectronic device can be divided into two subgroups, internal and external. Both of them require some certain material properties to be calculated. For example, software packets computing inner efficiency requires lattice parameters, while software's computing external efficiencies require refractive index and absorption coefficients. efficiencies require refractive index and absorption coefficients. However, it is not always possible to find these values within the literature, since even doping or array concentrations critically affects material parameters. Here, we use density functional theory softwares in our computations. Optionally, it is possible to analyze temperature and pressure effects and optical properties by these software packages. The crystal and density structure calculations were sequentially performed by Hello everyone, I am Bilgehan Barışoner from Gazi University Department of Physics, which is located in Ankara, Turkey. My presentation will be about light extraction efficiency enhancement of indium gallium nitride near ultraviolet LEDs by genetic algorithm. Now, please let me begin by the main content of this presentation. The first section will be a brief introduction, actually the motivation and the concept of our study. Later on, I will introduce the main schematics of indium gallium nitride-based light-emitting devices. The next slides will actually be a detailed motivation of the study. Also, the material and methods will be given at the same time. We have used an optimization algorithm and efficiency calculations, which will be explained in the section of optimization method, and then corresponding results will be shown. A discussion will be given, and then finally, I will conclude my presentation. The history of light-emitting diodes have begun almost 70 years ago by William Shockley. The spectrum of LEDs were within infrared spectrum back then until the invention of the first visible light-emitting diode, which was proposed by Nick Holonyak in 1962. Later on, the semiconductor technology has developed greatly such that LEDs have become available even in deep ultraviolet regions these days. The ultraviolet light-emitting diodes play an important role for many varieties of usage in semiconductor light technology, such as high-resolution data recording, white light illumination, combined fluorescence ultraviolet LED systems, and some other application areas in medicine and biochemistry. However, ultraviolet LEDs efficiencies diminish similarly as the operating frequency increases, such that efficiency improvement of these devices is still a popular topic in scientific researches. As well known, semiconductor technology is based on PN junctions, which can be evolved to PIN junction by inserting usually an undoped intermediate region. Therefore, light generation can be produced by radiative recombination mechanisms. And this mechanism should be supported by a substrate due to fabrication issues. This brings a lattice matching conflict between the substrate and the junction. Thus, an intermediate buffer layer is generally inevitable. Here, a problem arises on all standard LED designs such that emitted electromagnetic waves within the active region are not guided in general. This causes light to have arbitrary propagation directions. In this manner, we propose one-dimensional photoelectric crystals, namely distributed Bragg reflectors, to be utilized in the design to enhance the light extraction efficiency. Also, an electron blocking layer is strictly required to balance the current. And finally, we propose to reshape the surface by gratings to enhance the light output ratio. These gratings are supposed to serve the same role as an anti-reflection coating without a need of additional material. The efficiency of an optoelectronic device can be divided into two subgroups, internal and external. Both of them require some certain material properties to be calculated. For example, software packets computing inner efficiency requires lattice parameters, while softwares computing external efficiencies require refractive index and absorption coefficients. However, it is not always possible to find these values within the literature, since even doping or alloy concentrations critically affects material parameters. Here, we use density functional theory softwares in our computations. Optionally, it is possible to analyze temperature and pressure effects and optical properties by these software packages. The crystal and band structure calculations were sequentially performed by the custom simulation package to search for information on lattice match and optical parameters of the ultraviolet LED material components. The exchange correlation functional was set as PBE-SOL, which is a revised generalized gradient approximation with a good performance in determination of lattice properties of the compounds derived from 3, 4, and 5 groups. The ultra-soft potentials were preferred with 450 electrovolt energy cutoff for the plane wave basis set. Otherwise, on the basis of the main run with PBE-SOL, a separate exchange functional was used in non-self-consistent mode while analyzing the electronic and optical characteristics to get realistic data as possible. The bulk silicon carbide, aluminum nitride, and gallium nitride were constructed, and optimized unit cells have been given in this figure. Then, the P-type magnesium-doped gallium nitride and N-type silicon-doped gallium nitride were modeled with acceptor and donor concentrations of 1.45 10 to 21 and 1.36 10 to 21 inverse centimeters cubed respectively. Moreover, the resulting lattice constants, customized non-cost pack K point grid and energy gap values have been presented for these back layers of ultraviolet LED in the table 1. The obtained results, as seen in the table, show that lattice match is substantially satisfied for the considered material set. Mismatch percent values between silicon carbide and aluminum nitride and silicon-doped gallium nitride, and silicon-doped gallium nitride and magnesium-doped gallium nitride are 1.4, 2.5, and 0.06% respectively. We focused on two significant optical parameters, refractive index and extinction coefficient here. Then so the scissor operator within CASTEC was applied in the electronic structure along with the different non-local exchange function. Now, let us look at the optimization algorithm. We have used a conventional genetic algorithm in our study. The algorithm starts by generating total random designs in a certain amount. The parameters of these designs are assumed to be their chromosomes, and their values are limited as given in the previous slides. For example, all these purple individuals represent a different design here. Later on, the efficiency values of all these chromosomes are computed. If any of them satisfies a certain criteria, the code stops. Otherwise, it gets ready for the next cycle. A selection method is determined to match individuals to generate a new population. The method here can be fully optional. Here in this study, we have matched a couple of individuals such that they have adjacent efficiency rankings, and later the crossover. And later, after the crossover, a new generation joins the algorithm cycle. Here, in figure 3, the final optimized structure of gallium nitride-based light-emitting diode is given with an operating wavelength below 370 nanometer. Here, these animations show the two-dimensional, time-dependent amplitude distributions of the structure with and without bright reflectors, respectively. The obvious effect of the reflectors enabled the light extraction efficiency to increase from 17 to 44%. In this study, it is shown that a highly efficient near ultraviolet light-emitting diode device can be designed via only basic enhancements. The upper efficiency bands of these devices are limited by non-radiative recombination rates, absorption, and reflection phenomena. The main advantage of these indium gallium nitride quantum well-based devices is lattice matching. For example, The proposed materials are easy to obtain, and gallium nitride-based light-emitting diodes show similar lattice structures with silicon carbide substrates. However, the fabrication errors cause even more efficiency drop inevitably. In conclusion, even though both design and fabrication of ultraviolet electronic devices can be extremely improved, there are still some challenges to overcome. For example, current designs can be enhanced by implementation of alternative layers, or the designs can be handled in 2 or 3-dimensional modifications. Internal efficiencies of these devices are another design issue and can be enhanced via material-based modifications. Absorption and reflection affects the external quantum efficiency, and this study shows that they can be reduced dramatically, while non-radiative recombinations are out of the scope of this study. These real performance analyses of these designs should be realized after fabrication, since fabrication itself is another important part affecting the overall efficiency. Thank you for your attention.
Thank you very much, Mr. Dr. Öner. Your very nice presentation. Are you here? Dr. Öner, do you hear me? Oh, I think Dr. Öner cannot attend to the meeting. Dr. Okay.
Yes.
Ah.
I will present my screen if that is possible.
Yes, of course.
Should I start, Dr. Ali?
Sorry, I want to make some introduction about you, but yeah, I think I have one information about you. According to your website, you are known as the Assistant Professor of Electrical and Electronic Engineering in Bilkent University. And
I am actually visiting scholar at Stanford University now.
Okay.
Yes.
Your PhD and MS are also taken from Stanford University, isn't it?
Correct.
Good. And according to here, your research area are the physics and application of semiconductor devices, silicon germanium-based integrated optoelectronics, optical interconnection to silicon electronics, infrared detectors, plasmonic photovoltaics, and the semiconductor materials, atomic layer deposition, smart and reconfigurable devices and surfaces are your interest area. Is it correct?
Correct. Correct, Professor R.
Thank you. Now, would you please start your presentation?
Sure. Please let me know when you see my screen.
Yeah, it's seen very clearly.
Okay. All right. Hello, everybody. Thank you so much for inviting me to this conference, and I really appreciate the hard work of the organizers. So I'd like to start with that. And as Professor R mentioned, my name is Ali Okyay. I'm a visiting scholar at Stanford University. I'm going to talk about today a contribution to the growth of 3 nitrides using atomic layer deposition. In my talk, I'm going to give a brief introduction about myself and my company, which is building these tools, and also a small overview about atomic layer deposition, what it is. I'll present my contribution to this work, to this literature with my colleagues, and talk about some emerging applications where ALD could be important, and share some overview in the applications of ALD. So let's just start with that. I'm actually a visiting scholar at Stanford. I have been a professor at Bilkent University in Ankara between 2008 and 2016, during which we started a company on building ALD tools based on my research. And we have received some grants from the Turkish government to actually realize this technology. We also started a branch in United States. In my background, as Professor R mentioned, I work on semiconductor devices, especially optoelectronic devices. I also worked in Intel in Santa Clara on the 3D NAND technology. I was part of the team which produced the world's first QLC product. My company is merely focused on ALD technology. It is a scientific company doing a lot of research, collaboration with universities. We also build custom tools to enable this research. In our publications, during my tenure at Bilkent University, Turkey became number 6 in the number of plasma ALD publications in the world. And if you look at university institution-based, Bilkent University was number 1 in 2014 and in top 10 in 2015, thanks to our research contributions. So what is ALD and how is it different than other techniques? This table summarizes the advantages of ALD versus other technologies, which is listed here as molecular beam epitaxy, chemical vapor deposition, sputtering or PVD, evaporation, and PLD. Now, ALD has very good thickness uniformity down to atomic resolution. The film density with no pinholes is pretty good. Step coverage or conformality is one of the strong suits of ALD, which differentiates it from other techniques. And because it is a chemical process, the interface quality is often very good because of the chemical reaction forming at the surface. It is a relatively low temperature deposition technique. There's a growing research on ALD, even down to room temperature ALD is possible. There are, of course, some disadvantages of everything that is good. It comes with some limitations. The deposition rate in ALD is relatively slow compared to other techniques. This is simply based because of the atomic nature or monolayer by monolayer deposition nature of ALD. And industrial applicability, because this is a new technique and it is growing, industrial applicability is becoming more and more developed, but currently there are some techniques which are faster for industrial applications. Well, this is originally called atomic layer epitaxy and has been, we say it is a relatively new technology, but as you know, in the history of technology, something new is still 50 years old. It is a chemical vapor deposition technique where the reaction is split into 2 parts. And each part is self-limiting and occurs on the surface only. So we call this modified CVD because CVD, there are reactions in the gas phase and also in the surface, while ALD is only surface reaction based. So after the completion of two half reactions, system becomes stable again, and a monolayer of film has been deposited. One example process for ALD is the most common one that is being utilized today is aluminum oxide, is the reaction between trimetal aluminum, as shown here, the metal organic group. Surface is hydroxyl terminated, and when the trimetal aluminum comes to the surface, it is chemically chemisorbed to the surface by one of the ligands connecting or forming a bond with the hydroxyl group and forming a methane gas, which is volatile and removed from the environment, as shown in this figure. So the aluminum atom makes a bond to oxygen, forming the base of the aluminum oxide material. However, after this reaction, aluminum still has two metal organic ligands, two methyl groups that are remaining on the surface. So after this, this process is completed, the surface hydroxyl groups are all converted to aluminum oxygen bonds with metal groups attached to each aluminum atom. In order to remove the metal groups, water vapor is introduced to the chamber after the byproducts of the previous reaction is removed. Now, the water molecule has two hydrogen and one oxygen, where this oxygen becomes the source of aluminum oxide and a co-reactant, while the hydrogens are responsible to remove the remaining ligands on the aluminum atoms. By forming volatile methane molecules, water molecule removes the organics from the aluminum and actually forms aluminum oxide bonds. Once this reaction is completed, the surface becomes stable and a complete monolayer of aluminum oxide has formed on the surface with the same hydroxyl termination as before, which is ready now for the second monolayer. If you repeat this process cycles, you end up getting thicker and thicker films controlled by monolayer for each cycle of ALD process. ALD growth is a saturation-based reaction, and there's a sweet spot, sweet region for ALD process to occur. Now, this graph shows the growth cycle on the y-axis versus temperature on the x-axis. So there is a temperature window, which is called ALD window, where the growth rate is a constant irrespective of this temperature. This is where the surface reaction is self-limiting, and increasing the temperature does not promote any further reaction. If you look at the non-idealities from this window, for instance, for higher temperatures, if the reaction temperature is increased indefinitely, what we start to see is the temperature decomposes the surface species, which starts to increase the reaction rate as opposed to a constant. On another instance, the higher temperature in some cases promotes desorption of the surface species from the surface. That means the surface species start to leave the surface and the deposition rate goes down. And similarly, condensation limit and activation energy limit are the bottom boundaries for the ALD window temperature. For the case of aluminum oxide, for instance, ALD window is very wide, somewhere from 50 to 80 degrees all the way to 250 degrees. Now, the most highest strength of ALD technique, as opposed to other techniques, is it is thickness control, uniformity, and conformality. This illustration demonstrates the capabilities of ALD in its strongest suits. Now, if we have any sort of surface structure with a 3D aspect ratio to it, atomic layer deposition can actually conformally cover all the steps and even non-line of sight structures that are inside of this this microstructure with conformal and uniform coating. As opposed to other techniques, inside of this pocket will be shadowed or will actually have step coverage problems in different techniques. This is one of the most important merits of ALD technology. A typical ALD tool looks like this. In terms of graphical interface, you actually enter a recipe, which is a repetitive process, and then you are controlling gas flows, etc. So it is actually looks like a very standard system. Now, when you grow materials with ALD, we are interested in linearity. It's a very important property of ALD, which means as you increase the number of cycles, you get scaled thickness with the number of cycles. So this is a experimental result from one of our studies showing the number of cycles of an experiment versus the obtained thickness measured by external ellipsometer technique. When you look at these triangles as data points, they lie exactly on this line where you can extract growth per cycle for this recipe as around 1.29 angstroms per cycle. The uniformity across a big area is less than 1% variation in such a technique. These are some example materials that can be grown, but it is not limited to this. There's a lot of current research going on to develop new and new materials. Again, some uniformity examples of grown ALD films like titanium oxide, zinc oxide, platinum material, and even composite materials that are deposited on top of each other, laminated. Our contribution, which I will give more details about, is based on a new design of reactor. And in this design, we actually use a large area hollow cathode and a compact reactor design to improve efficiency. This increases the growth rate of the film, at the same time removes oxygen contamination, which is a very big problem for nitride growths. We also achieve better crystallinity, and we see crystal material as opposed to amorphous deposition. And we also achieve reduced plasma damage due to reduced number of ions in the reactor. So some applications and emerging areas of ALD and our collaboration work with some different universities. In this slide, you are looking at a MEMS chip, which is used for night vision cameras. We actually have a suspended structure, which is a resistor, and it is a MEMS structure which has to operate in vacuum. However, because of the vacuum process, there are residual gases which start to outgas from the underlying substrate. ALD was used to completely encapsulate and act as a diffusion barrier for this structure to eliminate the diffusion of residual gases. And only a 10, 15 nanometer kind of a thickness is sufficient to provide this effect. The challenge in this work was basically to be able to cover up the whole structure, as you as you imagine the arms and even the backside of this suspended structure conformally without any residual stress or strain to avoid any disruption of this mechanical, fragile mechanical structure. And ALD was the only technique that can do this conformally all around. In another work we published, we actually used ALD technique to coat a very thin zinc oxide layer around titanium oxide wires. If you look at a single wire, it's formed of titanium oxide, and titanium oxide has a slightly larger band gap compared to zinc oxide. And in order to have it work as a sensor, a UV sensor, or near UV sensor, you need to adjust the band gap. By applying a zinc oxide layer, we were able to show that very thin zinc oxide layer was able to reduce the effective band gap and promote the operation of such a sensor or the surface at near UV wavelengths. Another application where ALDs was used, again, for very high aspect ratio structures where we grow, again, titanium oxide wires and completely cover up with zinc oxide to change the surface properties. These structures have been used for photocatalytic applications, dye-synthesized solar cells, and similar sensor applications. Now these structures are also being utilized, researched for gas sensing applications. So ALD can cover without leaving a pinhole, is a continuous film around these kind of harsh structures. ALD's application is not only limited to inorganic materials, but it can also be used with organic materials such as peptides. This work actually is again from my group and collaboration, forming ultra thin sheet layers around 10-20 nanometer peptide structures, which are bases of proteins. And by doing so, we actually form hollow structures of metal oxides such as zinc oxide or titanium oxide or combination of that, and remove the organic material by calcination after the formation. This way it is possible to obtain narrow and hollow nanotubes of oxides for very large area applications. The applications of ALD is not only, again, limited to formation of oxides, but with our effort, we have introduced the significant contributions on nitride materials-based ALD. And before our work, there were only some reports of gallium nitride or aluminum nitride deposition efforts, which all ended up with some oxygen contamination in the film. We have demonstrated that we can actually obtain with a special design oxygen-free nitrides by ALD. And we actually developed a thin film transistor process to use this nitride layer as a channel material. The structure shown here is a back-gated thin film transistor with a silicon substrate acting as the gate, an aluminum oxide gate dielectric, and gallium nitride channel material. Source and drain are found as shown in the structure. Silicon oxide layers are used to isolate the transistors from each other. We have demonstrated that this device behaves like a transistor as shown in this family of ID-VDS curves. This was actually a very important result, and it is till today, it is the record low temperature for the realization of a gallium nitride transistor, which is below 200 Celsius. We also, because of this reduced temperature, we were also able to demonstrate such transistors, thin film transistors, on flexible substrates for application on IoT or mobile kind of devices. So again, the low temperature capability introduced here is a very big competition of ALD as opposed to traditional techniques which require nearly 1000 degrees Celsius to deposit gallium nitride material. Since now ALD provides a capability to grow materials on top of each other, now you can imagine growing three-dimensional structures or stacks of devices on top of each other. This work actually, again, from my group, has demonstrated that we can grow different layers or stacks of materials three-dimensionally and integrate them to form three-dimensional circuits with higher and higher density. Of course, in today's mobile and Internet of Things requirements, the more functionality and the more memory is desirable. So here again, two transistors are being illustrated with zinc oxide channels in this case as the electron conduction material, where the first transistor is directly formed on the substrate, and the second layer of transistors are formed on an SiO2 spacer layer. This proof of concept can be further improved to stack up more layers of materials on top of each other. We also looked at optical properties of gallium nitride materials deposited by ALD. As you know, gallium nitride is a direct bandgap material with bandgap suitable in the blue and near UV region. So we were able to characterize photodetectors made of such materials. We used 20 nanometers of gallium nitride and formed photodetectors in this interdigitated fashion. This curve shows the responsivity versus wavelength for such devices. And we were able to demonstrate that when we have a nitrogen and hydrogen annealed process, gallium nitride bandgap is recovered, as opposed to nitrogen annealed process. We have some nitrogen defects left in the material, which might be responsible from some trap states and the visible light or higher wavelengths absorption. So one of the most important contributions till today, which is unbeaten is, in the literature, is the reduction of oxygen contamination in nitride layers growth with ALD. What you are looking at is the reactor that we have, research reactor that we have used at Bilkent University. This is a commercial system that was purchased from a commercial vendor. However, it has an inductively coupled ICP plasma system, which looks like this shown here, a quartz tube with a coil around it. And because of the hydrogen process, the hydrogen plasma etches or removes oxygen from the quartz material, and in time it forms a hole or a punch through this quartz cylinder. This oxygen that is taken from the quartz eventually gets deposited into the material surface, which results in significant oxygen incorporation in the nitride material growth in the order of 20 to 30%. Our motivation was to reduce this oxygen incorporation by a complete custom design of the reactor with a new approach, where we used a hollow cathode plasma source and specially modified this for the commercial reactor. What we have seen is significant improvement in the oxygen incorporation, to reduce the oxygen incorporation. However, there are some challenges on incorporating or retrofitting a commercial system with a hollow cathode plasma, because the reactor is very large and the plasma source is very small. This means the plasma is being diluted significantly over the large area. And there is no capability for in situ monitoring of the reaction inside the reactor. So we have published some improvements, but the solution was to design the plasma reactor from scratch. This is what my company is about, actually. We designed a compact reactor with a large area source, and we have introduced in situ metrology technique to be able to understand the process that is happening on the surface. Now, this is a standard ALD approach with trimetal aluminum being introduced into the chamber. The chamber is evacuated by a vacuum pump, and plasma gases are introduced from another inlet through the hollow cathode plasma source, where the RF power is applied. The figure on the right shows a typical ALD cycle as it happens. The x-axis is time, and the y-axis, each of them are pressure and flow of gases. During the ALD cycle as it happens, the ellipsometer allows us to monitor the surface reactions as they're happening. These are the growth per cycle results versus different parameters optimized in the ALD process. Different colors demonstrate various substrate temperatures. If you look at the top left figure, growth per cycle increases with the duration of the plasma applied, and after 20 seconds in this figure, the increasing the plasma duration further does not contribute to growth per cycle. We call this the saturation of this parameter. Same thing happens with growth per cycle versus plasma power. For a fixed plasma duration, we increase the plasma power, and for low plasma powers, the growth per cycle is relatively low, owing to insufficient removal of ligands and incorporation of nitrogen. As we increase the plasma power, we see increasing rate of growth per cycle and a saturation after a certain plasma power. This is true for, this is a very characteristic property of ALD, with it is self-limiting and surface limiting process properties. If you look at the plasma power versus temperature impact, what you are looking at here is the single ALD cycle of the aluminum nitride deposition. The initial pulse of the precursor or the co-reactant increases the thickness measured by ellipsometer. This is due to chemisorption and some physisorb species attaching to the surface. And this is typically in the order of 2 to 3 angstroms. And now during the purge interval, where we let the not chemisorb samples species to be removed from the surface, we see a slight reduction in the thickness, which is due to removal of physisorbed species. At this boundary, around 18 seconds, plasma is turned on. With the plasma species coming into play, the ligands are removed with the argon and nitrogen atoms at the same time, hydrogen species interacting. The plasma results in incorporation of nitrogen, and at the end of the plasma cycle, we end up with a certain eventual thickness. Now, compared to the start, which is a reference to 0, depending on plasma power and the temperature of the process, we receive something around 1 to 1.5 angstroms per ALD cycle. At 200 Celsius, if you look at the similar properties, we get slightly higher deposition rate, but the top GPC is still saturated at 1.4, 1.5 angstroms per cycle. I want to concentrate you to these two figures here, which are for low plasma powers. What we see from the ellipsometer immediately is that when the plasma power is relatively low, it is insufficient to remove the ligands and cause incorporation. Therefore, the metal organic species remain on the surface, and when we actually bring the next cycle of pulsing of trimetal aluminum, we observe a smaller increase in the thickness because the surface is already covered with metal organics partially. These are the resulting film characteristics from the growth. I'd like to draw your attention first to this XRD graph on the right, where it shows different films grown from 100 to 250 Celsius temperature. As the temperature increases, we have seen that the as grown film starts to behave in some crystalline form as opposed to amorphous deposition. This is also pretty new for ALD, where it is known to be depositing amorphous films. The crystalline nature of this film is improved with temperature, but we are limited with 250 Celsius with our reactor, so we could not investigate further increase in temperature. We are currently trying to do that. And if you look at the properties of these films, optical and stoichiometric properties, as shown in these tables, they are very close to bulk properties, and the in situ metrology versus ex situ characterization are in good agreement. The bottom table shows the oxygen incorporation in these films and carbon contamination. measured by XPS technique. Carbon incorporation is below measurable level, and oxygen incorporation is shown to be reduced from 20 to 30% down to 3 atomic percent in the films. The remaining oxygen incorporation, we assume, is attributed to the residual water vapor and oxygen that is remaining in the chamber. So in a brief summary, a commercial system with inductively coupled ICP plasma results actually in a low density film with non-stoichiometric aluminum to nitrogen ratio. And the deposition rate is relatively low at 0.6 angstroms, even at 300 watts. If you retrofit the commercial system with the hollow cathode design, with our hollow cathode design, we see that the film density increases and the stoichiometry is improved, together with a slight increase in the deposition rate. The custom design large area hollow cathode with compact reactor design, which is performed by my company, provides actually very high density films and stoichiometric films, even at very low plasma powers such as 100 watts. And the growth rate is almost double to 1.1 angstroms. I'd like to change gears at this time to talk about some emerging applications of atomic layer deposition on catalysis. For instance, nanoparticles are actually coated by ALD layers to change their surface properties and improve their catalysis efficiency. In this case, what you're seeing is a palladium particle being coated by platinum ALD process. And because of the three-dimensional coating capability, ALD can conformally cover all around this particle. ALD's application also in photovoltaics is rapidly penetrating and rapidly taking part. Now, atomic aluminum oxide has been a very important passivation material for photovoltaic materials, and even now different oxide materials are being researched to provide passivation of the photovoltaic devices. What you are seeing here is actually a choice of materials for the passivation of a surface of a photovoltaic cell, depending on the orientation of the p-n junction. For p-type silicon, passivation is better with aluminum oxide, as shown here, and there are some other candidates. For, however, n-type silicon, there are less choices, and aluminum oxide is one of the important ones, and it is considered unique. And ALD is one of the only materials that can, one of the only methods that can conformally coat the pyramid structure on the surface of photovoltaic cells, which is shown here also for tandem cells, where there is a big surface structure as shown here with a pyramid-like light encapsulating layers. And ALD can coat these materials very conformally and without pinholes. It is also used as a buffer layer for advanced perovskite tandem solar cells. These research results are very recent from the following groups as quoted here and published in Nature journals, shows an ALD deposited tin oxide buffer layer between the crystalline silicon and perovskite tandem cells can actually improve the efficiency of such cells beyond 25%. And in this case, a very conformal ultra-thin layer is required, and a complete continuous coverage is very critical to avoid short circuit or leakage through such layers. Again, there has been a growing interest in the catalysis research domain, where very small particles need to be coated in their powder form. In addition to coating flat substrates and or solar cell surfaces, ALD is being researched for coating of powders, such as catalyst particles, where it has been shown in research that this could be a game-changing technology for future of energy storage and catalysis. The size control and the conformality offered by ALD comes with actually 4 main control structures. We actually are able to control the process by the temperature, the choice of precursor, the cycles, and the choice of substrate. This leads into also selective deposition of chemicals or films on desired surfaces, while other surfaces can be completely not coated. Okay, this example shows again a linearly controlled ALD cycles on particles, and shows the evolution of nucleation of ALD film as particles and then coalescence into a continuous film. The temperature plays an important role in the growth model. In this left figure, the temperature is kept as 100 Celsius, and very small islanding appears, and there's only a combination of adatom captures and growth of these islands. At higher temperatures, there's different processes also going on, like diffusion of nanoparticles on the surface and a bigger range of size distribution. The precursor is also plays an important role. In the interest of time, I will not go into detail of that, but in short, we can choose different precursors to deposit the same materials, and the chemistry there can be optimized. Okay. All right, so ALD, as we said, is very strong in deposition of ultra-thin layers. This is one example of elemental deposition of platinum on around a nanoparticle, where we can see under this TM image the formation of this monolayer. ALD's application for energy storage is also picking up great interest. Most of the problems or issues in batteries are now being researched to be addressed by ALD. One such problem is these micro cracks in nanoparticles used in batteries. In this work, ALD was used to cover or coat inside of these holes and cracks to increase the lifetime of the batteries and the cycling time of the batteries before the failure happens. Similar work with the same group has shown that ALD coating can suppress the formation of metallic structures that are detrimental for the process of batteries, and eliminate or slow down this formation of dendrites, dendrite-like structures. Finally, I would like to point out to a very interesting emerging area of ALD for deposition of two-dimensional transition metal dichalcogenides. Transition metal dichalcogenides nowadays are deposited using chemical vapor deposition techniques, and typically at 800 to 900 Celsius temperature on special substrates. After that, the two-dimensional material is transferred by using a layer transfer technology. A group in TU Eindhoven, led by Rinkessels and Agit Bol, has demonstrated that plasma ALD can be used to deposit two-dimensional materials such as molybdenum disulfide. This is one of the early results, and there are increasing interest in applying ALD to find ways to deposit two-dimensional materials on various surfaces. This will be an interesting thing to see for the upcoming years, how this technology evolves, as two-dimensional materials are predicted to become a very important game changer in VLSI electronics. I'd like to stop here and thank you for everybody for your attention, and I'd be happy to take some questions.
Thank you very much, Dr. Okay, for your nice and very fruitful presentation. It's really helpful, fruitful presentation. I checked the YouTube and also this for the question, but I cannot see any question now. Dr. Atesh?
Yeah, I would like to thank to Professor Ali Kemal Okyay, my dear colleague, my dear friend. His contribution very much to this area, especially related to ALD study, laser ablations, and other their studies works very impressive us. I would like to thank to him and his team for their contribution to our universities and our country. Thank you, Ali Kemal Okyay.
Thank you.
Teşekkür ediyorum.
Thank you, Hakan.
Thank you. Dr. Atesh?
So I will stop sharing, Professor R.
Dr. Munir Naife, our last speaker. Is there any connection?
He couldn't connect until now because of the internet problem. Probably we can close the session. Before closing this session, if you want some small speech, or Ali
Yes.
or other professor, you can give a small talk.
Yes, before closing this session, I want to thank very much for the attendees and their contribution, for the speakers, especially their very esteemed and very fruitful presentations. But a special thanks for the organizing committee and also the technical staff which help me with all the connection to the Zoom and other presentations. Therefore, I want to thanks and express my special thanks for the whole organizing committee. Good evening.
Good evening.